The nearest star is 4 light-years away, and by honest physics, it might as well be a different universe. Proxima Centauri is our cosmic next door, yet every real number turns soon into decades, generations, or never. So what would it actually take to send humans there, and why does the closest destination still break our engines, our bodies, and our energy budget? Imagine a voyage where the first enemy is not distance but arithmetic, cold, precise, and indifferent. In that ledger, every kilogram becomes a promise, and every promise demands payment in fire. On screen, the map looks merciful. One small red star, one thin line, one tempting world. But the universe does not negotiate with desire. It only accepts momentum, shielding, and time. To reach another sun with people aboard, you must build a machine that is also a habitat, a hospital, and a courtroom. Then trust it to endure decades without rescue or revision. You must carry an ecosystem that never pauses, while every valve, seal, and sensor slowly drifts toward failure. And you must do it in a medium that is not truly empty. A few stray atoms become bullets at speed, and a grain of dust becomes a test of armor. Radiation is not a single dramatic event here. It is a constant weather system, writing its effects into tissue and electronics one invisible strike at a time. Even the simple act of staying sane becomes engineering, because isolation is not a mood, it is an environment. This film follows the hard constraints that hide behind the poetry of nearby stars, the equations that punish low exhaust velocity, the energy that scales beyond intuition, and the heat that must be rejected into vacuum without mercy. We will weigh propulsion concepts that almost close the gap, and we will examine why almost can still mean an unlivable mission. We will ask what it takes to keep a crew alive when replacement parts are not shipments, but decisions made years earlier. Along the way, we will meet ideas that seem to cheat the problem, pushing without carrying fuel, riding light itself, until their own requirements come into focus. Each chapter tightens the accounting, not to extinguish wonder, but to clarify its price. Because the nearest star is not merely a destination, it is a measure of what humanity is willing to become to cross the dark. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. We begin with the seduction of a nearby world, then descend through propulsion, survival, radiation, and the modern wager of laser sails. And by the end, the meaning of close will feel less like geography and more like a verdict. Proxima Centauri sits in our sky like a promise that feels almost personal, a faint red point hidden in the southern constellation Centaurus. It is the closest star beyond the Sun, the one that makes interstellar travel sound reasonable, almost practical, if you say the word closest slowly enough. Astronomers can point to it, measure it, and name a planet beside it, and that act of naming makes the void feel negotiable. Proxima b is roughly Earth-sized, and it orbits in the star's so-called habitable zone, where starlight could allow liquid water. That single fact invites a dangerous thought, because water is the keyword that turns curiosity into longing. Maybe the next world is not a fantasy. Maybe it is simply far. Then the numbers arrive and the spell breaks, because astronomy is where romance goes to be audited. Proxima Centauri is about 4.24 light-years away, and the phrase is so familiar that it can sound like a time estimate. It is not a poetic unit, and it is not a promise about travel time. It is a distance, the length light covers in a year while moving at nature's speed limit. In kilometers, that separation is about 4.01 times 10 to the 13, a figure that looks more like a bank password than a route. Written out, it is a 4 followed by 13 zeros, and our brains do not keep their footing on that cliff. We replace scale with metaphor, and metaphors lie, softly, convincingly, and with a smile. Even the idea of nearest is a trick of perspective, because the nearest star is still outside the Sun's gravitational neighborhood. The heliosphere, that vast bubble carved by the solar wind, reaches far beyond the planets before it thins into interstellar space. Proxima waits beyond that boundary, in a region where the Sun is only one bright star among many. When you look at the night sky, you see a dome of lights that feels close enough to touch. In reality, you are seeing a deep field of distances, stacked along your line of sight like layers of transparent glass. We can say the distance another way and still fail to feel it, because language is too small for vacuum. If Earth were a grain of sand, Proxima would still be across a continent, and the ocean between would still be mostly nothing. If the solar system were shrunk to a room, the nearest star would be another building, and the street between would hold no air at all. Every comparison is a confession that our intuition was built for forests and shorelines, not for interstellar emptiness. Space is not a map with blank areas. Space is the blank, and the islands are rare. A useful reminder hides in the way starlight behaves, because light itself becomes a ruler. The photons reaching your eyes tonight left Proxima more than 4 years ago, when events on Earth were already history. If Proxima flared yesterday, we would not know for years, and that delay is not a technical problem. It is the geometry of the universe, and it sets the rhythm of every conversation across the stars. Even radio, even laser pulses, even the fastest signal we can send must crawl across those 4 light years at sea. Proxima b sharpens the emotional stake because it sounds like a destination rather than a statistic. It is close enough to be named, close enough to be drawn in artist impressions, close enough to be argued over in papers and press releases. It might be rocky, with an iron core and silicate crust, because planets of that size often are. It might have an atmosphere, perhaps thin and battered, perhaps dense and cloudy, and we cannot yet smell it from here. It might be tidally locked, with one face always lit and one face always dark, and that simple orbital fact would shape everything from winds to weather. The twilight ring between day and night could be gentle or violent, depending on how heat moves through air and ocean. Its star is a red dwarf, a small and cool M-type star that sips its fuel and lives for trillions of years. Red dwarfs are the most common stars in the Milky Way, which is why they matter to the search for life. Yet they are also temperamental, especially when young, and Proxima is known to flare. In a flare, magnetic fields snap and reconnect, hurling radiation and charged particles outward like shrapnel. Those outbursts can strip atmospheres over time, erode ozone, and sterilize exposed surfaces, especially when a planet orbits close enough to be in the habitable zone of a dim star. Habitability is already uncertain, even before we ask a harder question. Can we reach it with real machines and real bodies? This documentary sets a rule at the door. No warp drives, no hyperspace, no hand-waved breakthroughs that ignore mass, energy, and heat. We will only use propulsion that can be described with physics we already trust, the kind that survives peer review and laboratory tests. We will only use life support that can be engineered, maintained, and repaired, not imagined as a magic box. We will only use humans as they are, vulnerable to radiation, isolation, and time, and we will treat those vulnerabilities as design constraints. With that rule, the nearest star stops being a dream and becomes an accounting problem, where every hope has a number attached. Distance is the first line item, because distance sets the minimum time even before you choose an engine. The second line item is speed, because speed sets the energy cost and the violence of every collision. The third line item is survival, because time turns every system into a failure mode, and failure in deep space is unforgiving. The fourth line item is arrival, because arriving is not the same as passing by, and a destination you cannot stop at is only a spectacle. To understand the trap, start with what we have actually launched, not what we can sketch on a napkin. Voyager 1 is a small, tough machine that has been flying since 1977, built with 1970s electronics and a stubborn kind of redundancy. It is now far beyond the outer planets, still talking in a whisper, still moving through the thin plasma between stars. Its cruise speed relative to the Sun is about 17 kilometers per second, and that number sounds fast until you compare it to light. At that pace, a straight line to Proxima Centauri would take roughly 73,000 years, even if nothing broke and the trajectory were perfect. That is longer than recorded history. It is longer than the age of agriculture. It is longer than any civilization has ever lasted without transforming into something unrecognizable. The fastest human-made object is not a starship, and it is not a weapon. It is the Parker Solar Probe, built to fall toward the Sun and steal speed from gravity, diving through the corona where heat and radiation punish every surface. At its peak, it exceeds 190 kilometers per second, a record that sounds like victory because it is so far beyond our everyday scale. Even if you could aim that speed outward and keep it, without the Sun's gravity continually helping, it would still need about 6,700 years to reach Proxima. That is not a mission. That is a geological process, longer than the rise and fall of empires, longer than the lifespan of most languages. These benchmarks are not chosen to mock our engineering because they represent triumphs of precision and endurance. They are chosen because they are real, measured by tracking stations, confirmed by telemetry, and paid for with decades of work. They are the best we have done with hardware that exists, tested in space, and verified by the slow honesty of distance. They show that interstellar distance is not a small extension of interplanetary travel. It is a different category of problem, where the baseline is not years but millennia, and where nearby becomes a word with no human meaning. At this point, the mind tries a shortcut, because the mind hates helplessness. What if we go much faster? What if we chase a fraction of a light speed, not as a metaphor but as a design target? Light travels about 300,000 kilometers per second, and it does not need fuel to do it. 10% of that is 30,000 kilometers per second, a number that sounds like science fiction, and yet is only 0.1 c. At 0.1 c, the trip to Proxima is still more than 42 years one way, and that is the clean number with no detours. That is before you slow down. That is before you carry food, air, water, shielding, spare parts, and people. The light year confuses us because it smuggles time into distance, and the brain grabs the wrong half. We hear 4.24 light years and we imagine 4 years, as if the ship were a beam of light. But the ship is not light. The ship is mass, and mass demands energy, and energy demands a power source you can actually build. Every extra kilometer per second is paid for in propellant, in power, or in some clever exchange with a planet or a star. Gravity assists can help inside a solar system, where planets offer moving wells of gravity to borrow from. Between stars, there is nothing to steal from but your own fuel, and the interstellar medium does not offer discounts. Even if we could build a craft that reaches 0.1 c, we would meet the next wall, and it is a wall made of timing. A flyby is not an arrival, because speed turns the destination into a blur. A flyby at 0.1 c crosses a planetary system in hours, and the window for close observations is painfully brief. It gives you data, not a landing, and not a settlement. If Proxima b is the goal, you must slow down enough to stay, to orbit, to descend, to choose a site. That means you must cancel most of your speed, and cancellation is not a philosophical concept. Deceleration is not optional. It is the price of touching another world. This is where the arithmetic turns cruel, because it doubles the hardest part. Every interstellar mission pays an energy tax twice, and the invoice comes due whether you are ready or not. First, you accelerate to cruise speed, pushing against your own inertia until the stars begin to shift. Then you decelerate back down, safely with control, while the destination grows from a dot into a system. The same delta V that makes the trip possible must be bought again at the end, and the second purchase happens when you are far from home and out of second chances. If your propulsion system is hard to scale for acceleration, it is equally hard to scale for braking. The hardest part is not reaching high speed. The hardest part is reaching high speed and still having the means to stop. On paper, rockets can do anything if you allow enough propellant, because equations do not get tired. In reality, propellant has mass, and mass demands more propellant to push it, and the loop tightens like a noose. This is the tyranny of the rocket equation, a rule that punishes ambition with exponential costs. For chemical rockets, the exhaust speed is too low, so the required propellant becomes absurd long before you approach interstellar fractions of c. For nuclear thermal, the exhaust is better, but still not close to what interstellar speeds demand for a crewed ship. For electric propulsion, the exhaust can be high, but the thrust is tiny, and the power system becomes the bottleneck that sets the pace. So the story quickly becomes about energy, because energy is what speed really means. How much energy is required to push a habitat, shielding, and supplies to a meaningful fraction of c without tearing the structure apart? Where does that energy come from, and how is it stored over decades without catastrophic loss? How is it converted into momentum without melting the engine or the ship? Because high power has a thermal signature. How do you radiate waste heat into a vacuum that refuses to carry it away, where the only way to cool is to glow? The physics does not care about our optimism, and it does not negotiate. Then comes the biological bill, and it arrives with compound interest. At interstellar speeds, the space between stars is not empty enough to be safe, because almost nothing, is still something at 30,000 kilometers per second. A grain of dust at 0.1 C hits with explosive energy, closer to a bomb than a pebble. A stray atom becomes a radiation event, and a thin gas becomes a constant sandblaster of particles. Cosmic rays and solar particles accumulate dose over years, and shielding adds mass, and mass demands more energy. Microgravity weakens bone and muscle, and rotation adds engineering complexity, because spinning habitats introduce structural loads and moving parts. Isolation becomes a medical variable, not a poetic one, because minds are biological too. A crew is not cargo. A crew is a living system that degrades. Time makes every risk compound, because long missions turn rare failures into inevitabilities. A 40-year cruise means decades of maintenance without resupply, while every seal, valve and circuit ages in silence. Electronics must survive radiation and still be repairable by humans with limited tools, not replaced by a shipment from Earth. Mechanical parts must be redundant, but redundancy adds mass, and mass raises the energy bill again. Software must be stable, but it must also adapt to failures no one predicted, because the ship will become its own ecosystem of glitches. A closed environment must recycle air and water with near-perfect reliability, and near-perfect is a brutal standard. Even small leaks become fatal when the nearest spare is 4 light-years away. Closed-loop life support is not a single machine, and it is not a single discipline. It is a chain of systems that must work together for decades, like organs that cannot afford to sleep. Carbon dioxide removal, oxygen generation, water recovery, waste processing, food production, and microbial control must all be stable, and stability must survive human error. A greenhouse can feed people, but it also introduces pests, disease, and fragile dependencies, because biology brings its own surprises. Stored food simplifies biology, but it increases mass and limits mission duration, and vitamins do not last forever. Every choice is a trade between weight, reliability, and human health, and every trade has consequences that appear years later. The seductive part of Proxima b is that it gives the journey a reason, and reasons are what humans use to endure. A planet in the habitable zone suggests oceans, soil, and a second home, even if that picture is only an artist's light on a dark canvas. But reachability is a separate question from habitability, and the two can drift apart. A world can be perfect and still be unreachable, simply because the energy cost is beyond our industrial capacity. A world can be reachable and still be lethal, because radiation, atmosphere loss, or chemistry can turn Earth-sized into Earth-hostile. The nearest star forces us to separate desire from engineering and ask what we mean by possible. So Chapter 1 ends where the real story begins. Proxima Centauri is close only by cosmic standards, not by human ones, and that distinction matters. The distance is 4.01 times 10 to the 13 kilometers, and our fastest probes still need thousands of years, even when they ride gravity like a slingshot. Even at 0.1 C, the trip consumes a lifetime, and the mission must still break, which means it must carry the ability to undo its own speed. Speed is only the first wall. Stopping safely is the second. Surviving the time in between is the third, and each wall is built from the same materials: energy, mass, and heat. In the next chapter, we stop pretending distance is the only problem, because distance is merely the opening move. We ask what propulsion could plausibly buy us decades instead of millennia, without breaking the laws we already know. We follow the energy, the mass, and the heat, because those numbers decide what dreams can move, and which ones must remain stories. Chapter 1 left us with distance as an opening move, not the whole game. 4.24 light-years is not only far, it is far in a way that turns propulsion into a verdict. On a star map it looks like a short hop, one bright neighbour beside another. In engineering terms, it is a canyon you cannot jump by running harder. Interplanetary travel taught us a comforting lesson, and it is a lesson written into every launch video. If you need more speed, you bring more fuel. If you need more fuel, you build a bigger rocket. That logic works inside a solar system because the required speed changes are measured in single-digit, sometimes double-digit, kilometers per second. Those numbers are large to humans, yet they remain small to physics. We learn to treat space like a place where patience substitutes for power. We coast for months, we wait for planetary alignments, and we accept that a probe can take years to reach the outer planets. The solar system rewards cleverness, gravity assists, aerobraking, and trajectories that sip delta V. It is a domain where time can be traded for fuel, and where mistakes can sometimes be corrected. Even when we miss a target, we often miss it slowly enough to try again. Interstellar travel breaks that intuition, because the speeds that matter are a different species. 10% of light speed is 30,000 kilometers per second. That is not a small upgrade over Voyager. It is a leap that drags every hidden cost into the open: mass, energy, heat, and risk. The moment you say 0.1c, you stop talking like a mission planner and start talking like an industrial economist. Even the language we use begins to shift. In planetary flight, we talk about missions and launch windows. For interstellar flight, we start talking about fractions of c and energy budgets that sound like national infrastructure. The nearest star forces us to stop thinking like travelers and start thinking like builders of moving worlds. It also forces a harder question: what counts as a reasonable vehicle when the destination is a lifetime away? The first tool is a simple equation with a brutal personality. The Tsiolkovsky rocket equation links delta V to exhaust velocity and mass ratio. It says your achievable change in velocity grows with exhaust speed and with the logarithm of how much mass you throw away. This is not an opinion, and it is not a policy choice. It is conservation of momentum written in the language of engines. Historically, the equation arrived before most rockets did. Konstantin Tsiolkovsky derived it in the early 20th century, when powered flight itself was still young. He imagined space travel with the calm certainty of a mathematician, and then he wrote down the constraint that would haunt it. The irony is sharp. The dream came with its own warning label. Later pioneers, from Goddard to von Braun, would build hardware that confirmed his quiet algebra. The idea is accessible even if the math feels distant. A rocket moves forward by throwing mass backward. To go faster, it must throw more mass away, or throw it faster. If it must throw more mass, it must carry that mass first, and carrying it makes the rocket heavier. The engine is not just pushing a payload, it is pushing the fuel that will push the payload later. In plain terms, you pay interest on every kilogram you bring. That feedback loop is the trap. Each extra increment of delta V demands a larger propellant fraction. Past a point, the rocket becomes mostly propellant pushing propellant, with a shrinking island of payload at the top. In diagrams, the payload looks like a capstone. In reality, it becomes a rounding error. The vehicle's silhouette turns into tanks, plumbing, and insulation, with the people reduced to a small protected cavity. The equation does not care about heroism or budgets. It is exponential in the way that matters to engineers. When you stack maneuvers, the mass ratios multiply and the payload collapses. A mission profile that looks reasonable as a list of burns becomes impossible when you add the compounding. The spreadsheet does not argue, and it does not get tired. It is worth pausing on that word, logarithm, because it hides the cruelty. Logarithms grow slowly, which sounds friendly at first, yet the rocket equation uses the logarithm in reverse, because the mass ratio must grow exponentially to buy linear delta V. The price is not proportional. The price accelerates. The last few percent of speed can cost more propellant than everything before it. For a crewed mission, you do not buy delta V once. You buy it at least twice. You accelerate to cruise, then you decelerate to arrive. If you want margin, you buy it again for course corrections, abort options, and contingencies. Each just in case is sensible in isolation, and devastating in combination. This is why interstellar plans often die in the margins, not in the headline number. In the solar system, we often accept one-way probes. We accept flybys that never slow down and orbiters that never land. A human mission cannot accept that indifference. Humans are not data packets. They must arrive alive, and they must be able to stop. They also must arrive with enough capability left to survive the first day, not merely the last second. Chemical rockets sit at the bottom of this hierarchy because their exhaust velocity is limited by chemistry. Specific impulse is a measure of how efficiently a rocket uses propellant. For chemical propulsion, it peaks in the hundreds of seconds, which corresponds to only a few kilometers per second of effective exhaust speed. That number is not a failure of engineering. It is a boundary set by molecular bonds. The energy available per kilogram is impressive for Earth, yet modest against interstellar velocity. A chemical engine is a controlled explosion, and its exhaust is hot gas. The molecules can only carry so much energy before they dissociate. The nozzle can only convert so much thermal energy into directed flow. Even the best combinations, hydrogen and oxygen, carefully cooled and expanded, still live in the same neighborhood of performance. The exhaust is fast by everyday standards, but slow compared to the speeds we now demand. That exhaust speed is wonderful for leaving Earth. It is enough to climb out of a gravity well, reach orbit, and push probes to the outer planets with clever trajectories. It is not enough to push a large mass to interstellar cruise speeds without absurd propellant fractions. Earth to orbit is a sprint. Interstellar travel is a marathon run at sprint speed. The same tool that wins one race collapses in the other. The numbers turn grotesque quickly. If your exhaust speed is a few kilometers per second, and your required delta V is tens of thousands of kilometers per second, the mass ratio becomes astronomical. The rocket equation forces you into a vehicle that is effectively all fuel, with no room left for people. The ship becomes a fuel tank with a story attached, and the story ends when you ask where the tanks end. To visualize it, imagine a stack of stages rising like a tower at dusk. Each stage is mostly propellant, and each stage exists to lift the propellant above it. The payload, where the crew would live, is a tiny bright window at the top. Now imagine adding more speed, and watching that window shrink until it disappears. The camera pulls back, and the ship becomes a thin line of tanks fading into darkness. Even if you accept staging, the problem does not disappear. Staging resets the equation by dropping empty tanks and engines. It helps, but it cannot change the underlying need for enormous total propellant mass when exhaust velocity is low. Staging is a clever accounting trick. It is not a new physics. It also assumes flawless separations because a single failed stage can strand everything above it. There is also a practical ceiling to staging. Each stage needs engines, plumbing, separation systems, guidance, and structural margins. Each separation event is a risk, and each stage adds complexity that must work perfectly. When the number of stages climbs, reliability falls. Quietly, mathematically, and without mercy. The vehicle becomes less like a ship and more like a chain of bombs that must detonate in order. Inside the solar system, we often avoid carrying all the energy ourselves. We borrow it from planets through gravity assists. Between stars, there are no convenient moving worlds to steal momentum from. The ship must bring its own delta V, or it must find a way to avoid carrying propellant. Interstellar space is not a highway with on-ramps. It is open ocean with no ports. The nearest help is not a rescue mission, but another star. This is why chemical propulsion peaks at planetary travel. It is a near-perfect tool for short, intense burns and high thrust. It is a poor tool for sustained, high delta V missions where every kilogram multiplies. Chemistry is powerful in a gravity well. It is weak against an interstellar timetable. The tyranny begins when the timetable stops being negotiable. The rocket equation also exposes a deeper truth. Propulsion is not only about fuel mass, it is about energy, because exhaust velocity is ultimately an energy conversion problem. A higher exhaust speed means you're giving more kinetic energy to the exhaust, and you must get that energy from somewhere. Momentum sets the direction of the trade, but energy sets the cost. To reach a cruise speed, the ship must carry kinetic energy, and kinetic energy scales with the square of velocity at low speeds. Doubling speed quadruples the energy. That is why speed is expensive even before relativity enters the room. It is not a metaphor, it is a curve. The curve is gentle at first, then it steepens until it feels like a wall. At a tenth of light speed, the energy is no longer a mission scale number. It becomes a civilization scale number. The kinetic energy of a modestly massive crewed ship at 0.1 C rivals the annual energy use of nations depending on ship mass and efficiency. And that is only the energy in the moving mass, not the losses, not the heat, not the inefficiencies. If you imagine braking at the far end, you nearly double the bill. Consider what that means visually. A spacecraft coasting in silence carries an invisible reservoir of energy, locked into its motion. In a hangar, energy is stored in fuel tanks. In interstellar flight, energy is stored in velocity, like a bullet that never stops being fired. The hull is quiet, the crew sleeps, and the energy remains poised in every kilogram. Relativity sharpens the penalty as you climb higher. At small fractions of C, classical formulas are close enough. As you push toward higher fractions, the relativistic kinetic energy rises faster than intuition expects, and the bookkeeping gets harsher. Time dilation is the famous effect, but energy is the one that empties your ledger. It is the difference between a daring plan and an impossible one. Even at 0.1 c, relativistic corrections are not dominant, yet they are a warning. They tell you the slope is steepening ahead. If voyousancy already strains our industrial capacity, what happens at 0.2 c, or Wosterkomsak, when the energy curve bends upward more aggressively? The numbers do not negotiate. They simply demand that you pay in power plants, in fuel, or in time. Energy is not only what you need to accelerate, it is also what you must manage as heat. Any real engine wastes energy, and waste energy becomes waste heat, inside a ship that cannot dump it into air or water. In space there is no breeze, no ocean, and no convection, only radiation. Even the warmest machinery sits in a cold void that refuses to help. Vacuum is not cold in the way people mean it. Vacuum is indifferent. The only way to reject heat is to radiate it away as infrared light. That requires large radiator area, and radiator area is mass, structure, and vulnerability. A radiator is not a magic panel. It is a thin, exposed organ. It must survive micrometeoroids, radiation damage, and decades of thermal cycling. High-power propulsion implies high heat rejection. If you run a powerful reactor or a high-power electric thruster system, you must carry radiators sized for continuous operation. If you cannot reject heat, you must throttle down, and then your trip time grows. The ship becomes constrained by its ability to glow. In the visuals, the dark craft sprouts broad, delicate fins that shimmer faintly in infrared. Radiators also create a design paradox. You want them large to stay cool. You want them small to reduce mass and cross-section. You want them robust against impacts, but robustness adds mass that the rocket equation punishes. They are wings you cannot flap, and shields you cannot thicken without paying twice. The ship's most fragile surfaces become the ones it cannot live without. There is a second paradox hidden inside the first. Hotter radiators can reject more heat per square meter, because radiated power rises steeply with temperature. Yet hotter radiators demand materials that survive high temperatures for decades. They also increase infrared brightness, which can be a liability if you care about detectability. Even if you do not, brightness is still wasted energy, leaving us light. Now the payload itself starts to mutate. A human mission is not a probe with a camera. It is a moving habitat with biology inside, and biology is heavy. Humans require pressure, temperature control, hygiene, and protection from radiation. They also require something less measurable, stability over time. A machine can be shut down and restarted, but a crew cannot be paused. Start with the crew compartment and pressure hull. Add structure, micrometeoroid protection, and redundancy for decades of fatigue. Add power generation, power storage, and distribution that can survive faults without external help. A deep space ship cannot call for a tow. It must be its own shipyard. The design begins to resemble a submarine that can never surface. Then add life support that actually closes the loop. Air revitalization, water recovery, waste processing, and long-duration food strategies all require hardware, spares, and monitoring. Each subsystem needs margin because failure is not an inconvenience at 4 light years. A single stuck valve is not a maintenance ticket. It is a countdown. The quiet hum of fans and pumps becomes the sound of survival. Closed-loop life support sounds elegant, but it is a web of chemistry and biology. Carbon dioxide must be removed and oxygen restored. Trace contaminants must be scrubbed before they accumulate. Microbes must be managed, because a sealed habitat becomes an ecosystem whether you want it or not. Even dust, skin cells, and humidity become engineering variables that shape health. Food is not only calories, it is nutrition stability over decades, and that means either stored food with degradation risk, or onboard agriculture with its own mass and failure modes. Both options increase payload mass, and payload mass multiplies propellant needs. Even packaging becomes a design choice when you cannot resupply. The pantry becomes a long-term archive, and archives always grow heavy. Long storage brings quiet problems. Vitamins degrade, fats oxidize, and textures change in ways that affect appetite. Appetite matters because morale matters, and morale affects performance. The ship is not only a machine, it is a long experiment in human endurance. When the days blur together, a meal is not fuel, it is time marked in taste. Medical capability is not optional, and it is not light. You need diagnostics, pharmaceuticals, surgical tools, and training. You need the ability to handle trauma, infection, and chronic disease without evacuation. In a sense, the ship must carry a small hospital, compressed into mass and power budgets. It also must carry knowledge, because the crew may face conditions no one has treated in flight before. Spare parts are not optional either. Long missions turn improbable failures into expected ones. Every pump, valve, filter, and circuit that can fail must be repairable, and repairability requires tools, parts, and human labor. A spacecraft designed for months can rely on luck. A spacecraft designed for decades must rely on inventory. The storeroom becomes a second engine because it keeps the first one alive. Redundancy is not simply duplication, it is architecture. It is the ability to isolate faults, reroute power, and keep operating in degraded modes. That means extra wiring, extra sensors, extra software, and extra testing. Each addition is rational. Together they become heavy. The ship's nervous system thickens until it rivals the muscles. Radiation protection is where the mass creep becomes obvious. Outside Earth's magnetosphere, cosmic rays and solar particle events accumulate dose. Over decades, that dose becomes a mission-limiting hazard. Radiation is invisible, yet it writes itself into DNA. It also writes itself into electronics, slowly degrading materials and memory. Galactic cosmic rays are not just radiation in the casual sense. They include high-energy nuclei, atoms stripped and accelerated by distant astrophysical events. When they strike shielding, they can generate secondary particles, including neutrons that complicate protection. The shield can become a source of new radiation if it is poorly chosen. Protection becomes a materials science problem, not just a thickness problem. Shielding can be passive, like water, polyethylene, or regolith, which means mass. Shielding can be active, like magnetic or electric fields, which means power, complexity, and still some mass. Either way, protection is paid for in kilograms. The crew's safety is measured in aerial density and engineering trade-offs. The visuals shift from heroic hull plates to layered cross-sections, each layer bought with propellant. Those kilograms do not sit alone. Every kilogram of shielding requires more structure to hold it. More structure requires more propulsion capability. More propulsion capability often requires more power and more propellant, and the cycle tightens. The ship grows like a living thing, adding layers to survive. The tyranny is that survival systems and propulsion systems inflate each other. Even the choice to simulate gravity has a mass cost. Rotation can reduce bone loss and muscle wasting. Rotation also introduces bearings, joints, structural loads, and control systems that must run for decades without catastrophic failure. A spinning habitat is not just a ring. It is a machine under constant stress. Every rotation is a reminder that comfort is also engineering. And then there is the human factor, which engineers cannot ignore. A long mission must manage circadian rhythms, mental health, conflict, and boredom. That implies private space, sound control, lighting systems, and recreational capacity. These are not luxuries in a multi-decade confinement. They are stability systems for the mind. The ship must be a habitat, not a cockpit stretched across years. The rocket equation makes mass creep contagious. A small increase in payload does not just add a small amount of propellant, it increases propellant, which increases tankage, which increases structure, which increases engine requirements, which increases propellant again. The spreadsheet becomes a spiral. Engineers call it a mass cascade, and it can destroy a design without a single dramatic failure. This is why engineers fear late mass growth more than almost anything. In deep space design, mass is not a line item. It is a multiplier, a forgotten bracket, an extra safety margin, a thicker cable. Each can echo through the entire vehicle. The tyranny is subtle, because each choice looks small until you add them all. Now add the interstellar medium, which sounds like emptiness until you add speed. Between stars there is thin gas and sparse dust. At low speeds it is negligible. At 0.1 C it becomes a continuous hazard field. The ship does not merely travel through space, it plows through it. The forward hull becomes a bow wave, not of water, but of particles and ionization. A single grain of dust at that speed carries enormous kinetic energy. It does not behave like sand. It behaves like a hypervelocity projectile that can crater, spall, and generate plasma on impact. The impact is not a bump. It is a localized explosion. The camera lingers on a tiny speck, then cuts to a flash against metal that blooms like lightning. even individual atoms become energetic. At high cruise speeds, collisions with hydrogen atoms produce radiation and erosion effects. The ship experiences a constant, invisible bombardment that scales with velocity. The front of the craft becomes a leading edge in a particle storm. Over years, that storm can sandblast coatings, embrittle surfaces, and slowly rewrite the ship's geometry. Imagine the visuals: a dark hull moving through a starfield, and ahead of it, a faint, ghostly glow. That glow is not a headlight. It is the signature of impacts and ionization, a reminder that empty space has substance when you hit it fast enough. The stars remain still, but the ship's forward edge flickers with a thin, unnatural aurora. Shielding against this is possible in concept, but it is not free. One approach is Whipple shielding, where a thin bumper layer breaks up incoming particles and a standoff distance spreads the debris before it hits the main wall. It is a clever use of geometry, turning a point impact into a diffuse spray. The principle is simple, yet the implementation becomes heavy at interstellar energies. Whipple shields work well for micrometeoroids in Earth orbit. At interstellar speeds, the energies are far higher, and the shield must be thicker, layered, and extended. That means more mass at the front of the ship, exactly where you least want it. The ship's nose becomes a sacrificial structure. In cross-section, the forward end looks less like a hull and more like armor with empty gaps. You can also imagine sacrificial forward shields, ice blocks, or dust clouds deployed ahead of the craft. Each concept trades one problem for another. You either carry the shield mass or you carry the system that deploys it, and both feed the rocket equation. Protection is never free. It is prepaid mass, and every kilogram you put in front must be accelerated for years. The hazard is not only puncture, impacts generate secondary radiation and electromagnetic pulses that can damage electronics. Protection then requires hardened systems, redundancy, and additional shielding, and the payload grows again. The ship becomes a layered fortress, and the fortress must still accelerate. The visuals shift from sleek science fiction to something more like a deep-sea vessel wrapped in armor. At this point, the engineering foundation becomes a kind of courtroom. Chemical rockets are called as witnesses, and they testify honestly. Their exhaust velocity is too low, their propellant requirements explode, their strengths are real, but their domain is planetary. The verdict is not emotional, it is arithmetic, and arithmetic is indifferent to ambition, so we look for ways to raise exhaust velocity. Nuclear thermal rockets heat propellant with a reactor, pushing specific impulse higher than chemical. That helps, but it still leaves you far from the exhaust speeds needed for interstellar delta V with reasonable mass ratios. It is an improvement, not an escape. The ship gets better, yet the wall remains. The historical context matters here, because nuclear thermal propulsion is not a new fantasy. It was studied seriously in the 20th century, when governments were willing to fund uncomfortable ideas. The promise was clear: higher exhaust velocity without exotic propellants. The obstacles were also clear: reactor materials, testing constraints, and political risk. The technology stalled not only on physics, but on the difficulty of proving safety on Earth. Electric propulsion can reach very high exhaust velocities by accelerating ions. That reduces propellant mass for a given delta V. The price is low thrust, and low thrust means long acceleration times and huge power demands. It is efficient, yet patient to a fault. It is the right answer for many robotic missions, and a brutal answer for a heavy crewed ship. With electric propulsion, the engine is not a roaring flame. It is a whisper of ions, a steady stream that can run for months. That is perfect for gentle spiral trajectories and station keeping. For pushing a massive crewed ship towards 0.1 C, the power system becomes the real engine. The visuals show a faint blue plume, almost invisible, backed by enormous radiators glowing dull red. Power demands bring us back to heat. A high-power electric system needs a reactor or massive solar arrays, and it needs radiators. The ship becomes a power plant with a crew module attached, and the mass budget strains. The engine room grows until it dwarfs the living room. The crew's habitat looks like a small capsule tethered to an industrial machine. Even if you solve propulsion, you still owe the kinetic energy bill. If you accelerate a large mass to 0.1 C, you store catastrophic energy in the vehicle. That energy must be controlled during burns, and it must be removed during braking. A small mistake becomes a large disaster when the stored energy is so high. The ship is not merely travelling, It is carrying a moving catastrophe that must remain perfectly contained. Braking is often forgotten because it is less romantic than launch. But arrival is where the rocket equation becomes merciless. If you carry propellant to slow down, you must also accelerate that propellant during the outbound burn. The fuel for stopping is also fuel you must push for years. This is where optimistic sketches turn into blank spaces. This is the part that breaks casual plans. People imagine a ship that accelerates, coasts, and then simply arrives. But arrival is not a location. Arrival is a velocity relative to the destination. If you cannot shed that velocity, you do not arrive. You pass through. The destination becomes a blur of planets and light, seen once and then lost. If you plan to brake using the destination environment, you face constraints. Aerobraking needs an atmosphere, and Proxima B may not have a safe one. Magnetic sails and plasma braking need time, area, and favourable conditions. They also need reliability at the far end of a journey. A braking system that fails after decades is not a minor malfunction, it is the end of the mission. Every braking method is a negotiation with physics. If you cannot brake, you do not have a mission to a planet. You have a fast flyby through a star system that you cannot stay in. The difference is everything: science, settlement, survival. It is the difference between visiting and merely witnessing. So the chapter's logic closes in. Interstellar travel is not blocked by a single missing invention. It is blocked by a stack of coupled penalties that reinforce each other. Each penalty is manageable alone. Together they behave like a wall. The wall is built from equations that do not care how badly we want to cross. The rocket equation punishes low exhaust velocity with exponential propellant mass. Energy accounting punishes high speed with quadratic, then relativistic growth in required energy. Thermal management punishes high power with radiator mass and fragility. These are not separate problems. They are one problem wearing different masks. Solve one mask and another tightens. Human survival punishes long duration with redundancy, shielding, and life support mass. The interstellar medium punishes high speed with impact hazards that demand even more shielding. Each penalty adds mass, and mass feeds back into propulsion. The ship's requirements do not add, they multiply. That multiplication is the tyranny, because it turns reasonable needs into impossible totals. This is the tyranny. The closer you look, the more the problem becomes self-amplifying. The ship is not only moving through space, it is dragging a growing web of requirements behind it. In the end, the web can outweigh the purpose, and it invites an uncomfortable observation. Perhaps the nearest star is not far away, but we're still energetically small. Yet the central question remains, and it becomes sharper here. What would it truly take, by real physics and real engineering, to send humans to Proxima Centauri? Why does the nearest star still overwhelm our technology, biology, and energy limits? What does it say about our species that the closest neighbour is still, effectively, out of reach? Is the barrier primarily technical, or is it a mirror held up to our scale? The honest answer begins with a dark premise. If carrying propellant is the core trap, then the escape route is to stop carrying it, or to carry an energy source so dense that propellant becomes a secondary detail. That premise is not optimism, it is triage. It is the moment the narrative pivots from bigger rockets to different bargains. That premise points toward a different class of ideas: beamed energy that pushes a sail so the ship does not haul its own reaction mass. Fusion or antimatter that offers far higher energy density than chemistry. External braking concepts that use fields and plasma instead of onboard fuel. Each is a bargain offered by physics, and each demands payment elsewhere. The payments are not small, and they are not always in money. These candidates are not miracles. They are still constrained by mass, heat, and reliability. But they attack the root of the exponential problem by changing where the momentum exchange happens. They try to move the burden off the ship, onto a beam, onto a reaction, onto the environment, and in doing so, they shift the tyranny rather than erase it. So Chapter 2 ends with a question that is more threat than invitation. If the best rockets we know collapse under the rocket equation, what kind of propulsion could possibly carry humans across 4 light years? And if we find such propulsion, what new tyrannies will replace the old one? The next chapter turns from familiar engines to unfamiliar bargains. We follow the concepts that try to outrun the equation, and we ask what they demand in return. Chapter 2 ended with a question that is more threat than invitation. If rockets collapse under the equation, we must change the bargain, because the old bargain is simple and it is merciless. The first serious interstellar concepts do not whisper, and they never pretend to be gentle. They detonate, or they burn like a star in a bottle, and the visuals match the ambition: metal giants, hard shadows, and light that looks almost sacred. In archival sketches, the ships are drawn like monuments, their proportions closer to architecture than aviation. Even before the math, they announce a philosophy: if distance is the enemy, then power becomes the language. Nuclear pulse propulsion begins with a blunt idea, almost offensively direct in its simplicity. Throw nuclear bombs behind the ship and ride the blast, not once, but as a measured drumbeat that turns apocalypse into a metronome. The engine is not a flame, but a sequence, and sequence becomes control. The Orion-style concept uses repeated nuclear detonations behind a massive pusher plate. Each explosion becomes a discrete push, converted into forward momentum through a system that treats shock as a resource. Instead of continuous thrust, you get punctuation, thousands of violent commas that add up to a sentence written in velocity. In diagrams, it looks almost childish: plate, springs, bombs, until you imagine scale. The ship is a moving city, and behind it is a controlled chain of suns. The pulses are spaced, timed, and engineered, yet the energy source remains the same one that once defined the most terrifying century in human history. A pusher plate sits at the rear like an armoured drumhead. It is broad, thick, and blunt by necessity, because the impulse arrives as a hammer blow of plasma and debris. In motion, you can picture the plate flashing, briefly haloed by ionized gas, then returning to darkness as the next device slides into position. Between that plate and the rest of the vehicle is a shock absorber system. It turns millisecond impulses into tolerable acceleration for structure and crew by stretching the violence over seconds. The physics is brutally practical. Impulses force over time, so time is the only mercy you can buy. That stretching is not comfort, it is survival. Without it, the ship would be shaken apart by its own engine, and the crew would be injured by acceleration spikes. Even if the average acceleration looks modest on paper, the peaks would be jagged enough to break bones and snap trusses. This is why Orion is still discussed with a kind of awe. It offers both high thrust and high effective specific impulse, a rare combination that chemical rockets can never reach together. Chemical engines can be strong or efficient, but not both at once, because chemistry is trapped in the shallow energy of molecular bonds. High thrust matters because it shortens the time you spend spiraling outward from the sun. It lets a heavy ship accelerate hard without waiting months for tiny electric thrust to add up. It also changes mission geometry because you can leave the deep gravity well quickly, instead of lingering where every failure is still a public spectacle. High effective specific impulse matters because exhaust velocity is the escape hatch from exponential propellant. Nuclear devices can drive exhaust speeds far beyond chemical limits because they tap nuclear binding energy instead of molecular bonds. In plain terms, you stop paying for speed with mountains of fuel, and you start paying with engineering and politics instead. In chemical propulsion, the exhaust is hot gas pushed through a nozzle. In Orion, the exhaust is a rapidly expanding plasma cloud, shaped and timed so the plate catches momentum rather than raw heat. The coupling is everything, because you want the momentum to arrive as a push, not as a melt. This is the conceptual trick. Orion is not a rocket in the usual sense. It is more like a hammer that strikes the ship forward, again and again, until velocity becomes a new environment. The ship does not sip propellant, it consumes events. Historically, Orion emerged in the late 1950s and early 1960s, when nuclear optimism and nuclear dread shared the same calendar. The idea was studied seriously, with real engineering teams and real calculations, because the space age had just begun and limits still felt negotiable. In that era, the boundary between impossible and unfunded was not always clear. In the most optimistic studies, pulse propulsion could push a large craft to a few % of light speed. That sounds like victory until you translate it into human years, and then the numbers turn cold. The star does not care that the engine is dramatic, because distance is indifferent to spectacle. At 1% of light speed, Proxima remains more than 4 centuries away. At 5%, the one-way time still lands in many decades, and decades are long enough for entire institutions to change. A mission can outlive its sponsors, its language, and even the culture that launched it. Even if you accept aggressive acceleration, you still must coast for a long time. A crewed mission becomes a multi-decade commitment with no resupply and no rescue, and that absence changes what mission planning even means. It becomes less like a voyage and more like a sealed experiment in continuity. Orion's promise is not only speed, it is the ability to move a truly massive payload, including shielding, life support, redundancy, and the kind of spare parts that turn breakdowns into repairs. When every kilogram is a survival margin, payload is not luxury, it is probability. That payload capacity is the seductive part because human survival systems are heavy. A fast, tiny capsule is not a habitat, and a habitat is not light, especially when it must be self-contained for a lifetime. Water, air processing, food storage, medical gear, and radiation shelters all add up, and they do not negotiate with optimism. In the Orion imagination, you see the ship in silhouette, a thick plate at the back, a long spine forward, and at the nose a protected living volume, tucked behind layers like a seed inside a shell. The camera would linger on that spine, a long truss disappearing into shadow, while the next pulse unit waits like a bead on a string. Then the engineering reality arrives, and it is not romantic. Orion is a machine built to be hit by nuclear explosions thousands of times, and to remain aligned, functional, and sane afterward. The design is not about surviving one blast, but about surviving fatigue, repetition, and the slow erosion of tolerances. The pusher plate must survive repeated plasma impacts. It needs sacrificial coatings, clever geometry, and materials that resist ablation and cracking, because each pulse tries to sandblast the surface into vapor. The plasma is not a smooth wave, but a chaotic front of ions, fragments, and radiation that arrives with brutal indifference. Ablation is not just surface loss, it is performance loss. If the plate erodes unevenly, impulse coupling changes, and the ship begins to feel its own engine as wobble. Over thousands of pulses, that wobble can become a steering problem, and steering problems become trajectory errors. Designers talk about oil films, graphite layers, or replaceable tiles. Each solution is a new subsystem, and each subsystem is another promise that must hold for years. Every promise has a failure mode, and in deep space, failure modes do not stay small. Each pulse sends a shock through the plate and into the ship. The shock absorbers must cycle reliably for years without catastrophic fatigue, and fatigue is patient. It waits until a tiny crack becomes a mission-ending fracture. The danger is not the obvious break, but the invisible damage that accumulates quietly, pulse after pulse. The absorber stack is often drawn as giant pistons and springs. In reality, it would be a carefully tuned mechanical system, engineered to avoid resonance that could amplify vibration instead of damping it. A structure can ring like a bell, and a bell struck thousands of times will eventually change its shape. The vehicle is not just a plate and springs, it is a complex stack of magazines, bomb handling systems, timing electronics, and blast-shaping hardware, all operating in vacuum with no room for improvisation. The choreography must be precise, because the engine is a sequence, and sequences fail when timing slips. The bombs are not generic warheads, they are engineered pulse units designed to direct energy into propellant and reduce plate damage, because an undirected blast wastes energy and increases destruction. In many concepts, the device is paired with a shaped channel of material, so the expanding plasma is biased into a useful direction. That propellant can be a thin disk of material that becomes plasma when the device fires. The goal is to turn nuclear energy into a fast-moving mass that transfers momentum efficiently to the plate. Momentum transfer is the currency here, and the entire design is an attempt to spend energy without burning the bank. In this sense, Orion is a propulsion factory. Every pulse unit is a precision product, and the ship's acceleration is the output of an assembly line that must never miss a beat. The engine is not built once, it is manufactured continuously in the act of flight. That design requirement multiplies the program scale. You're not building a rocket, you're building an industrial line for nuclear pulse charges, and then trusting that line with human lives. The ship becomes inseparable from the civilization that feeds it, because the engine is a supply chain made physical. Now the political constraint becomes physical. Launching nuclear devices from Earth is effectively banned by treaties and public reality, and those constraints are not abstract when the payload is a bomb. The mere act of preparing such a mission would be interpreted as intent, and intent is a kind of fuel that nations burn quickly. The historical shadow matters here. Orion was studied in an era when atmospheric nuclear tests were still recent memory, and the world had already learned what fallout means in bones and soil. Strontium and cesium were not metaphors, they were measurements, and the planet had already paid for the lesson. Even ground testing is politically radioactive. Fallout is not a side effect, it is a global veto, because the byproducts do not respect borders or timelines. A propulsion breakthrough that poisons the commons is not a breakthrough, it is a confession of priorities. So Orion quietly moves off the launch pad and into orbit. The only plausible assembly site is space, where detonations do not poison air and soil, and where the vacuum changes how blast energy couples. In vacuum there is no shockwave in air, but momentum still exists, and radiation still travels without apology. But assembling an Orion vehicle in orbit is not a footnote. It implies heavy lift infrastructure, orbital shipyards, and nuclear materials handling at scale, all operating with the scrutiny of every nation. The visuals become industrial, cranes in slow motion, modules docking like vertebrae, and sealed containers moving with ceremonial caution. It also implies a new safety regime. A single accident in Earth orbit becomes a geopolitical crisis, not merely a mission failure, because debris and contamination would be shared by the entire planet. Even a non-nuclear collision would scatter high-value hardware into dangerous orbits, and the cleanup would be measured in decades. Even if you assemble it, you must still depart the inner solar system without detonating near Earth. That pushes the first pulses outward, complicating mission design and forcing a slow, careful prelude. The ship must crawl away under conventional propulsion, carrying its thunder like a secret, until distance makes the first flash tolerable. You can picture the departure sequence as a kind of ritual. The ship drifts away under conventional propulsion, silent and cautious, until distance makes the first flash acceptable. Then the first pulse blooms behind it, brief, white, and absolute, and the ship begins to move like something newly awakened. There is also the question of what the exhaust actually is. Orion does not throw hot gas from a nozzle. It throws plasma and debris from shaped charges, and that debris does not politely disappear. In space, exhaust becomes a cloud of fast matter, expanding into a region that other missions may someday want to occupy. That debris is energetic and radioactive. It contaminates any nearby space environment and creates hazards for other spacecraft, because the wake is not merely heat, it is material moving at extreme speed. The particles spread, thin out, and persist, and the timescales are long enough to matter to future traffic. In low Earth orbit, that would be unthinkable. In deep space, it is still a choice with consequences, because future traffic lanes and scientific instruments would share the same void. The emptiness between planets is not empty to a sensor, and it is not empty to a fragile surface. The engineering can be sketched, but the logistics are brutal. How many pulse units do you need for a meaningful fraction of C, and how many opportunities for failure does that number imply? The question is not only mass, but statistics, because reliability becomes a probability distribution stretched across years. The answer is usually thousands to tens of thousands, depending on mass and target velocity. Each unit must be stored, protected, and fed reliably into the firing sequence like ammunition for a war that lasts months. The magazine becomes a spine of risk, because every device is both propulsion and potential catastrophe. Storage is not trivial. The ship must keep the units secure against vibration, radiation, and micrometeoroid impacts, because one damaged device is not just lost performance, it is a hazard inside your own hull. You also need handling machinery that never drops a unit, never misaligns it, and never forgets what it is carrying. Reliability becomes existential. A jammed feed mechanism is not a minor anomaly, because it can strand the ship with no way to complete its acceleration profile. In a conventional rocket, you can shut down and still be near help, but here help is a memory, and stranded in interstellar terms is a special kind of word. It means coasting into darkness with no ability to change the ending, while the destination remains impossibly far. The crew would watch the stars shift slowly, knowing the ship has become a thrown object rather than a guided one. Guidance is also different. Each pulse is an impulse that can introduce pointing errors, bending loads, and vibration that propagates through the structure like a struck bell. The navigation system must treat every detonation as both thrust and disturbance, correcting continuously while the ship is being hit from behind. If the ship is even slightly misaligned, pulses can push it off axis. Over thousands of firings, tiny errors can accumulate into a trajectory that misses the target star by astronomical distances. At interstellar ranges, a miss is not a near miss, because the target is a point and the void is wide. A crewed ship must isolate the habitat from the worst of that vibration. That isolation adds mass and complexity, which the rocket equation still punishes, even when your engine is nuclear. The ship becomes a compromise between stiffness for alignment and softness for survival, and compromises are where failures like to hide. Orion also raises a moral question that cannot be engineered away. It normalizes nuclear detonations as routine propulsion, and routine changes what a civilization considers acceptable. When the extraordinary becomes scheduled, the psychological barriers erode, and the line between exploration and militarization blurs. A civilization willing to do that must accept a new relationship with weapons, treaties, and risk. The engine is also a political statement, one that would be heard long before the ship ever leaves. Even the planning would echo, because the infrastructure resembles capability, and capability invites suspicion. Yet the concept remains important because it shows a boundary. With known physics, you can plausibly reach percent-level light speed with high thrust, and that plausibility is a kind of map. It tells us where the cliffs are, and it tells us what price tags begin to look like when we demand more than chemistry can give. Percent-level light speed is not interstellar comfort. It is interstellar triage, turning millennia into decades or centuries, and forcing us to admit what we are truly asking of the people on board. What kind of society sends a crew on a mission that may outlast their entire adult lives, and what does it owe them in return? And even in the best case, Orion does not solve the arrival problem. High thrust helps you accelerate, but it also makes your braking bill larger, because velocity is a debt that must be paid down. The faster you go, the more energy you must remove, and energy removal is propulsion in reverse. If you carry pulse units to slow down, you must accelerate those pulse units for the entire outbound leg. The mass penalty returns at the worst moment, when you discover you packed your own anchor. The ship becomes heavier precisely because you want it to stop, and stopping is not optional if you want a destination. You can imagine braking by turning the ship and firing pulses forward. That works in principle, but it doubles the number of devices and doubles the risk, because every additional unit is another chance for failure. It also doubles the operational time under repeated shocks, and time under shock is time spent aging. You can imagine arriving as a flyby instead. That avoids braking, but it turns Proxima into a brief encounter, not a destination, and the crew becomes a witness rather than a visitor. The star system would be a window that closes as soon as it appears, and the mission would be defined by passing rather than arriving. So Orion is both a near solution and a trap. It buys speed and payload, then demands politics, infrastructure, and a second full propulsion system for stopping, and those demands arrive with compound interest. The engine can be built in theory, but the world required to build it is the harder construction. If nuclear pulse is the loud answer, fusion is the elegant one. Fusion promises star-level energy density without literal bombs, and it does so with a kind of scientific purity that feels inevitable. The visuals change here, from brutal flashes to contained light, blue-white plasma threaded by magnetic lines like invisible scaffolding. Fusion begins with a simple fact. Fusing light nuclei releases energy because the products have lower mass than the reactants, and the difference emerges as energy according to E equals mc squared. The numbers are small in mass and enormous in consequence, and that mismatch is what makes fusion feel like a door. That missing mass becomes energy, and the conversion is far more potent than chemical bonds. It is why stars shine, and why fusion looks like destiny, even when destiny is still an engineering problem. In the laboratory, it is not a gentle glow, but a fight against temperature, pressure, and instability. For propulsion, the attraction is direct. High energy density can support high exhaust velocity, which reduces propellant mass for a given delta V, and that reduction is the closest thing to magic the rocket equation allows. It does not repeal the equation, but it changes the coefficients, and coefficients decide feasibility. A fusion rocket aims to turn fusion energy into a directed exhaust stream. If you can do that efficiently, interstellar travel stops looking like pure fantasy and starts looking like a brutal project plan. The plan is still brutal, but it is no longer immediately absurd. The problem is hidden in the phrase, "if you can do that." Controlled fusion is not a solved engineering problem even for stationary power plants, and a rocket must do it while shaking, aging, and moving. It must perform in an environment where repairs are slow, parts are finite, and every subsystem is already stressed. A rocket engine is harsher than a power plant. It must ignite repeatedly, manage plasma instabilities, and survive intense radiation while accelerating a vehicle, and it must do all of it without a maintenance crew on Earth. The engine must be both laboratory and machine, and those two identities rarely coexist peacefully. Many fusion rocket concepts rely on inertial confinement. Tiny fuel pellets are compressed and heated until they fuse, then the products are directed for thrust through magnetic nozzles or shaped chambers. The pellets are like miniature stars that exist for an instant, and the engine is a factory that must create that instant again and again. That implies an ignition system with extreme repetition. You do not light one pellet, you light many per second for months, and the cadence must be as steady as a heartbeat. A heartbeat can tolerate variation, but an engine at these energies has less forgiveness, and the tolerances narrow as power rises. Pellet injection must be precise, timing must be exact, because a pellet that arrives late or off-center can turn a controlled burn into an asymmetric blast that hammers the chamber walls. In a cutaway, you would see the injector like a metronome, firing tiny spheres into a bright focal point that never stops demanding accuracy. A misfire is not only lost thrust, it can damage the chamber and destabilize the burn sequence. The engine must be robust against imperfection, yet perfection is what it demands. This is the paradox of high-energy systems. They require reliability most where reliability is hardest. Confinement is its own wall. Magnetic fields can bottle-charge plasma, but the plasma fights back with turbulence and instabilities, because at fusion temperatures matter behaves like a restless fluid of charges. The field lines are not walls in the everyday sense, and the plasma constantly tries to leak through every weakness. In a propulsion system, you also need an exhaust path. You must open the bottle in a controlled direction without losing confinement entirely, and that balancing act is the heart of the design. Too closed, and you cannot get thrust. Too open, and you lose the reaction before it pays you back. Then neutrons enter the story and darken it. Many practical fusion reactions produce fast neutrons that ignore magnetic fields, and those neutrons carry a large fraction of the energy. They leave the reaction zone like invisible shrapnel, and they do not care about your elegant magnetic architecture. Neutrons slam into structure, heating it and damaging it by displacing atoms. Over time, they embrittle metals, degrade composites, and ruin electronics, and the damage accumulates silently. A component can look intact while its crystal lattice becomes a weakened memory of what it was. Neutron radiation also creates activation. Parts become radioactive, complicating maintenance and forcing remote handling even inside your own ship, because the engine turns its surroundings into a slow hazard. The ship can become its own contaminated environment, requiring internal protocols that feel more like a reactor facility than a spacecraft. If you choose neutronic reactions, the physics becomes less forgiving. The required temperatures rise and ignition becomes harder, not easier, because the reaction cross-sections demand more extreme conditions. You trade one kind of damage for another kind of difficulty, and the trade is never free. So fusion propulsion is a trade. You can reduce neutron damage, but you pay with more demanding plasma conditions and more complex ignition, and the ship's reliability budget gets spent either way. The dream stays the same, but the engineering ledger changes columns. Even if you achieve fusion, you must convert its energy into thrust. Some energy emerges as charged particles you can direct with fields, and those particles are the cleanest path to useful momentum. The ideal is a magnetic nozzle that turns particle motion into a focused exhaust, like a flashlight beam made of ions. Some emerges as heat in the chamber walls. That heat must be rejected, and in space rejection means radiators, because there is no air to carry heat away. The vacuum is a perfect insulator for convection, so the only exit is photons, and photons leave at the speed of light but only in limited quantity. At fusion power levels, radiators stop being accessories. They become major ship structures sized by Stefan Boltzmann reality, and they must operate for years without puncture or warping. Visually, they are dark wings unfolding into the void, broad surfaces glowing faintly in infrared, broadcasting the ship's waste heat to the universe. If you run cooler radiators, they must be enormous. If you run hotter radiators, materials must survive years at punishing temperatures, and thermal cycling becomes a slow mechanical attack. Every expansion and contraction is a tiny stress test, repeated until something gives. Radiators also increase cross-section. Cross-section increases impact risk at high cruise speed, which pushes you toward more shielding, and shielding pushes you toward more mass. The ship begins to look less like a dart and more like a layered organism, with vulnerable membranes that must be protected without becoming impossibly heavy. Shielding is not only for the crew, it is for the engine, the electronics, and the radiators themselves, because a single puncture can cascade into overheating and shutdown. In a long mission, shutdown is not a pause, it is a potential end, because restarting may require conditions you can no longer create. A fusion ship becomes a layered compromise. You add shielding to survive radiation, then add power to push the shielding, then add radiators to cool the power, and the design begins to feel like a living organism. It is a creature built from metal and fields, and it survives by balancing flows it cannot ever stop. The mass cascade returns, just wearing a different mask. Fusion reduces propellant needs, but it does not erase structure, heat, and reliability, and those are the true long-duration tyrants. The rocket equation is still there, but now it shares the stage with thermodynamics and materials science. Then comes the fuel problem, and it is planetary in scale. Fusion is not limited by energy density alone. It is limited by what you can actually obtain, refine, and store without loss. A starship's fuel is not a tank you fill, it is an economy you build. Deuterium is abundant in water, but extracting it at scale is still industrial. It implies separation plants, energy input, quality control, and a supply chain that can support a mission that cannot turn back. Even abundant becomes a different word when you need it in quantities that reshape logistics. Helium-3 is rare on Earth and scarce in accessible deposits. It is often proposed because it can reduce neutron production in certain reactions, and that advantage tempts designers into fantasy supply chains. The fuel becomes a story we tell ourselves about what we will someday be able to mine. To get helium-3 in quantity, you look to the moon, to gas giant atmospheres, or to speculative deposits. Each option is a massive mining program, and mining programs have politics as well as physics. The mission's first step would not be a launch, but an industrial expansion into environments that do not forgive mistakes. Mining the moon implies processing vast regolith volumes for tiny concentrations. Scooping gas giants implies deep gravity wells and extreme engineering, because you must dive into radiation belts and climb back out. The fuel is not just rare, it is defended by the difficulty of reaching it. Even deuterium has storage challenges. Cryogenic handling over decades is not trivial, and boil-off is a slow leak that becomes a mission killer if you cannot reliquefy or recapture what escapes. A long voyage turns small losses into large consequences, because there is no refill station between stars. Some concepts store fusion fuel as pellets, each one a precision-manufactured component. That turns propellant into a stream of fragile, high-value parts, and it turns fuel loading into a manufacturing milestone. The ship's tanks become magazines again, and the engine becomes a consumer of perfect objects. A fusion mission is not only a ship, it is a supply chain that must deliver and certify millions of pellets, each with exact composition and geometry, because small deviations can change ignition behavior. The mission's reliability begins years before launch, in factories where tolerance is destiny. Ignition energy is another hidden cost. Each pellet needs a driver, often a laser or particle beam system, that must be efficient and durable across billions of pulses. The driver is itself a complex machine, and complex machines do not like to run continuously for years without maintenance. The driver produces waste heat. The power conditioning produces waste heat. The magnets produce waste heat, and the ship glows because it cannot hide its thermodynamics, even in the cold of interstellar space. In a thermal camera view, the ship would be a moving ember, a warm geometry against a background near absolute zero. At this point, fusion begins to resemble a flying power station. The crew module becomes a protected annex attached to an engine that never stops being dangerous, and the ship's layout becomes a map of hazards. The architecture is dictated by what must be kept away from what, and distance inside the ship becomes a form of shielding. And still, the travel time arithmetic is only partially softened. If you reach a few % of sea, you still face decades to Proxima, and decades are long enough for small problems to become civilizations. A minor design compromise can grow into a generational burden when time is the medium you travel through. Decades are not just calendar time, they are exposure time to radiation, to microgravity effects, to isolation, and to cumulative system failures, and each category multiplies the others. The ship is not only moving through space, it is moving through probability, and probability is never kind. A faster ship reduces exposure, but it increases other hazards. Higher speed raises impact energy with dust and gas, demanding stronger forward shielding, because even a grain becomes a bullet at these velocities. At a few percent of C, the kinetic energy of a tiny particle can rival explosives, and the ship must expect to be struck. Forward shielding at percent level C becomes heavy and thick. It must absorb hypervelocity impacts and manage secondary particle showers, as collisions create sprays of fragments and radiation that can penetrate deeper layers. The front of the ship becomes a sacrificial landscape, designed to erode gracefully rather than fail suddenly. That shielding must also protect the radiators and the reactor region, not only the crew. The ship's front becomes a sacrificial architecture, designed to be damaged in controlled ways rather than catastrophically. The design assumes harm will happen, and it tries to decide where the harm is allowed to land. Now we confront a quiet truth. Propulsion is not a single subsystem. It is an ecosystem of power, heat rejection, structure, and maintenance, and every part must survive the same long loneliness. The engine is not separate from the ship because the ship is built around the engine's consequences. Orion and fusion both attack the rocket equation by raising effective exhaust velocity. They both pay in complexity and in a kind of existential risk, because the margin for error shrinks as ambition rises. When the mission lasts decades, there is no such thing as a small flaw, only a flaw that has not matured yet. Orion pays in politics and in the normalization of nuclear detonations. Fusion pays in ignition difficulty, neutron damage, and a fuel economy that spans worlds, and neither bill is easy to settle. The engines are different in style, but they rhyme in their demands. Neither concept is a clean win. Both are engines that could almost do it, if almost were enough, and that almost is where human history tends to stall. The gap between a concept and a civilization-scale implementation is where dreams go to be audited, and even if one of them works, the mission still has to be lived. A crew must survive the cruise, not merely be accelerated into it, and survival is a system with its own equations. The engine can buy you speed, but it cannot buy you resilience, and resilience is what the calendar collects. Life support must run for decades without resupply. Medical capability must handle aging, injury, and disease in a sealed moving habitat, where a minor infection can become a strategic threat. In a closed environment, biology becomes logistics, and logistics becomes morality. Psychology becomes engineering. Conflict, boredom, and grief become failure modes that can cascade into operational mistakes, and mistakes in deep space have no external correction. The ship can be perfectly designed and still be undone by a tired decision made at the wrong hour. Radiation dose accumulates regardless of engine choice. Faster travel helps, but shielding and storm shelters still dominate mass and layout because the sun and the galaxy do not negotiate. The crew lives inside a geometry of protection, always aware that outside the walls the universe is quietly lethal. The ship must also remain repairable. Neutron damage, micrometeoroid erosion, and thermal cycling will steadily degrade materials, and degradation is the default state of matter under stress. The mission is not about preventing wear, but about managing it, anticipating it, and staying ahead of it. A mission plan must assume parts will fail. It must include tools, spares, fabrication capability, and procedures that work when the crew is tired, because fatigue is as real as any mechanical load. The ship must be a workshop as much as a vehicle, because the only maintenance depot is the one you bring with you. Then the final pivot arrives, and it is sobering. Even if you can accelerate, you still must slow down at the destination, and deceleration is not a bonus feature. The same physics that makes leaving possible makes arriving expensive, and the bill comes due at the farthest point from help. Braking at Proxima is not a detail. It is a second propulsion problem, solved far from Earth with no second chances, and the ship must arrive with the capability intact. If the braking system fails, the destination becomes a flyby by default, and default is a cruel planner. Carrying braking propellant doubles the mass penalty. Relying on external braking methods introduces huge structures and long braking distances, and long braking distances are long times exposed to the same hazards. A braking arc measured in years is still a journey, and journeys still break things. A magnetic sail could, in theory, push against the interstellar medium or the destination star's wind, but it requires enormous field structures and long time, and the field system must survive impacts while deployed. The sail is invisible but not invulnerable, and it must remain stable while the ship is still moving fast enough to be dangerous. A photon sail could break against starlight, but starlight at Proxima is weak. Weak pressure means large sails and long deceleration arcs, and large sails are delicate in a universe full of dust. The sail would be a vast, thin surface, and every micrometeoroid would be a test of whether thin can remain intact. Error braking is uncertain because Proxima B's atmosphere is unknown and likely harsh. Betting a crewed mission on an unknown atmosphere is not engineering, it is a wager made with human lives. Even if an atmosphere exists, its density, chemistry, and variability could turn braking into destruction. So the destination is not a finish line. It is another wall, built from the same materials as departure, and the wall does not care how heroic the journey felt. Arrival is a second act, and second acts are where missions often fail. This is the chapter's uneasy conclusion. Engines can buy speed, but speed is only one invoice, and the rest of the bill arrives in heat, mass, risk, and time. The propulsion dream is real, yet it drags behind it a long shadow of requirements that do not fit neatly on a blueprint. The nearest star remains an ocean of time, energy, and vulnerability. Closest is still a trick of perspective when humans must endure the crossing, and endurance is not infinite. The question is no longer only how to move a ship, but how to keep a world alive while it moves. The next chapter turns from engines to the people inside the hull. We ask what it takes to survive the cruise and what survival does to the mission. Chapter 3 ended with engines that could almost do it, and that word almost hides the real trap. If propulsion buys decades instead of centuries, the ship becomes a world that must endure decades alone. The camera lingers on a hull in darkness. No convoy behind it, no port ahead, only distance. A faint rim light traces antennae and radiator edges, as if the vehicle is already a small, drifting city. The central question sharpens inside the pressure shell where every breath is accounted for by pumps and chemistry. What would it truly take by real physics and real engineering to send humans to Proxima Centauri, and why does the nearest star still overwhelm us? The answer is not a single breakthrough, but a long chain of ordinary systems that must never stop. Each link is mundane on a checklist, yet merciless when it becomes the only thing between life and vacuum. A crewed interstellar vehicle is not a capsule with supplies, because supplies are a countdown with an expiration date. It is a closed industrial ecosystem that must run for 40 years without resupply, without evacuation, and without a maintenance depot. In that sense, the ship is less like a spacecraft and more like a remote research station welded shut, except the station is moving at interstellar speed. Even its dust, its smells, and its microbial film become part of the mission's infrastructure. Start with air, because air is time measured in minutes, and minutes are unforgiving. Oxygen must be generated continuously, carbon dioxide must be removed continuously, and both must keep working through failures, repairs, and the slow drift of sensors. Even small errors matter, because partial pressure is not an abstraction. It is the difference between clear thinking and panic. The body reads chemistry instantly, and it punishes mistakes without waiting for a meeting. On the ISS, oxygen comes from electrolysis, splitting water into oxygen and hydrogen with electrical power and careful control. The physics is simple, but the engineering is not, because bubbles, impurities, and electrode wear change performance over time. The oxygen must be dried, monitored, and delivered at stable pressure, while the hydrogen must be safely vented or recombined. The camera moves past stacked cells and braided hoses, quiet machinery doing violent chemistry in slow motion. CO2 is scrubbed by chemical beds and regenerable systems that alternately capture and vent carbon dioxide into space. Some systems use solid amines that bind CO2, then release it when heated or exposed to vacuum, and that cycling stresses seals and heaters. The scrubbing rate must match the crew's metabolic output, which rises during exercise and emergencies. In a sealed habitat, the air system is not background, it is a responsive organ. Even there, filters clog, valves stick, and parts are swapped by visiting cargo, while astronauts follow procedures written with ground teams watching. That quiet support is the invisible scaffolding of success, and it is easy to forget it exists. The ISS can afford to treat some failures as inconvenient, because Earth is close enough to forgive them. An interstellar ship has no such forgiveness, and inconvenience is how catastrophe begins. A true closed loop must also manage nitrogen and total pressure, because the atmosphere is not only oxygen. Nitrogen acts as a buffer gas that stabilizes breathing and reduces fire risk, and its pressure influences how gases dissolve in blood. The lesson is old, learned painfully from early spacecraft and submarines, because oxygen-rich atmospheres burn fast, and pressure mistakes injure silently. The camera cuts to archival footage of scorched panels, then returns to a modern gauge that cannot be allowed to drift. Leaks are inevitable over decades, and every lost molecule is a permanent loss without a replenishment tank. The visuals shift to a slow-motion plume, an invisible leak made visible by frost and light. A micrometeoroid pinhole, a fatigued seal, a hairline crack in a fitting. Each one is small, yet time makes it decisive. The ship is not fighting one dramatic breach. It is fighting the arithmetic of tiny losses. Over 40 years, even a tiny leak rate becomes a missing atmosphere, and missing atmosphere becomes a crisis that cannot be wished away. The crew does not experience it as a spreadsheet, but as a pressure gauge that refuses to hold steady. Somewhere behind a panel, a hiss becomes a clock. The camera lingers on a soap bubble test spreading across a seam, then trembling as it finds the floor. Trace contaminants are the slow poison of sealed habitats, and the danger arrives quietly. Ammonia from cleaners, formaldehyde from resins, solvents from maintenance, and off-gassed plastics from wiring insulation accumulate in the closed air. Some compounds irritate lungs, some affect cognition, and some interact in ways that only appear after months. A smell that seems harmless can be a chemical story that never stops being written. Catalytic oxidizers, charcoal beds, and sorbent cartridges become life-critical, because a little contamination is still contamination every day. In a small volume, the difference between safe and unsafe can be measured in parts per million. The camera glides past cartridge housings and sensor readouts, numbers that look calm until they begin to drift. A single digit rising slowly can be more frightening than an alarm, because it suggests a trend. In a sealed world, material science becomes medicine, because every polymer and adhesive has a chemical signature. Engineers must choose low outgassing components, bake them out, and still expect surprises as radiation and heat age the materials. The ship's air becomes a long-term experiment in indoor chemistry, and the crew lives inside the results. Even lubricants and insulation become biological variables, and the line between engineering and physiology blurs. Humidity control is not comfort. It is mold control and corrosion control, and it touches everything. Condensed water carries microbes and dissolved chemicals, so the air system becomes a sanitation system as well as a climate system. If humidity runs high, spores and biofilms find footholds. If it runs low, mucous membranes dry, and infection risk rises. The camera follows a bead of condensate along a duct, then into a hidden sump where life can quietly multiply. Water is the next clock, measured in days rather than minutes, and the arithmetic is merciless. Every kilogram of water you do not recycle becomes a kilogram you must launch, accelerate, shield, and protect for decades. In the visuals, water floats as glittering spheres, each one a tiny mass budget and a tiny promise. A hand reaches out and the droplet clings like a planet to a fingertip. The ISS recovers water from humidity condensate and urine, and it still depends on resupply for filters, pre-treatment chemicals, and replacement hardware. Even the best systems foul, because biology and dissolved minerals are relentless. That dependence is the warning label, because the ISS is a laboratory with a supply line, not a sealed world with no return. The camera shows a filter cartridge being swapped, and the gesture feels ordinary only because a cargo manifest exists. When a unit fails in orbit, a cargo vehicle can bring the next one, and that option vanishes beyond the moon. The camera watches a docking sequence in crisp sunlight, then cuts to a ship alone, where no approach lights will ever appear. The contrast is not dramatic music, it is physics and distance. Out there, logistics is not delayed, it is impossible. A Proxima ship must reclaim water with extreme closure, and closure is not a slogan, it is a number. It must distill, filter, and sterilize while keeping salts, pharmaceuticals, and microplastics from cycling endlessly through the crew. Otherwise, trace compounds become concentrated compounds, and concentrated compounds become chronic exposure. The same molecule can pass through a body, a pipe, and a filter 1,000 times, and each pass changes it slightly. The narrator's voice slows as the camera moves through translucent plumbing. Membranes foul, ion exchange resins saturate, ultraviolet lamps dim, and microbial fragments slip through if the system is not maintained. Sterilization must be layered, heat, UV, chemical oxidizers, because any single barrier will eventually fail. The ship learns the hard truth of public health. Safety is rarely one device, and more often a sequence. Even the sensors that guard purity degrade, and that is the unsettling part. A conductivity probe drifts, a flow meter misreads, and suddenly the system is correcting a problem that is not real. In long missions, measurement is not passive. It is an active part of survival. The camera holds on a calibration kit sealed like a relic because reference standards are the only anchor against drift. Waste processing is not a trash problem, it is a chemistry problem, and chemistry does not negotiate. Feces, food scraps, and packaging become feedstock, contamination risk, and a source of gases you must control. Even dry trash continues to react, releasing volatile compounds and harboring microbes that thrive in warm corners. The ship's refuse is not gone. It is merely stored in a different form, still alive with reactions. If waste is oxidized to CO2 and water, you close one loop but lose nutrients that plants need. If waste is composted or digested, you keep nutrients but invite microbial instability, odors, and pathogen management. Each pathway is a trade, simplicity versus recovery, controllability versus efficiency, and the ship must choose with no external safety net. The camera shows a sealed bioreactor tank, its surface quietly bubbling, like a swamp made industrial. Microbes are not passengers, they are stowaways that become residents, and they arrive on skin, food, and dust. In a sealed habitat, microbial ecology shifts toward whatever the environment rewards, not what humans prefer. The ship becomes a selective pressure chamber, and the winners are often the organisms that tolerate disinfectants and low nutrients. The crew's cleaning routine becomes an evolutionary force, shaping what survives in the walls. Biofilms grow in pipes and heat exchangers, and they change flow, heat transfer, and sensor accuracy over time. A small biofilm becomes a system-wide performance drift that looks like mystery, because the readings change before the cause is visible. The camera shows a transparent tube slowly clouding, then narrowing, then choking. In the background, a pump's pitch changes by a fraction, and that fraction is a warning. Closed-loop life support is often described as a set of boxes, like appliances in a row. In reality, it is a coupled network where one imbalance becomes another subsystem's overload, and overload becomes a cascade. If CO2 rises, crew performance drops. If crew performance drops, maintenance slips. If maintenance slips, failures multiply. The ship is a feedback machine, and humans are part of the circuitry. Reliability is the silent antagonist, because time multiplies failure, and the multiplication is cruel. A component with a small annual failure probability becomes a near certainty over 40 years, even if it looks good on paper. The ship does not need perfection for a week, it needs endurance for decades. This is why engineers fear the long tail, where probability stops being comforting and becomes a schedule. Engineers can quote mean time between failures, but the crew lives in the tail of the distribution, where bad luck accumulates. The mission is long enough that rare events stop being rare, and unlikely becomes eventual. A once-in-a-decade fault becomes 4 faults, and the 4th one arrives when you're already tired. The camera shows a maintenance log filling with identical entries, and the repetition feels like erosion. Redundancy is not optional, yet redundancy is not infinite, because mass and volume are not infinite. You can duplicate pumps and controllers, but you cannot duplicate every pipe, every seal, and every software dependency. Some parts are shared by necessity, and shared parts become single points of failure. The ship's design becomes a map of compromises, and every compromise has a shadow. Triple redundancy sounds comforting until you count parts and then count interfaces. More parts mean more joints, more sensors, more firmware, and more ways for a small fault to propagate. The visuals show a wiring harness branching like a nervous system. Beautiful, intricate, and vulnerable. A single connector, slightly oxidized, can become the seed of a system-wide mystery. The math compounds across subsystems in a way that feels unfair, yet it is ordinary probability. If air, water, power, and thermal control each have high reliability, the combined system reliability still falls as the product of probabilities. The ship is only as reliable as the least reliable interaction between its most reliable parts. A stable pump can still fail the mission if its sensor lies and the controller obeys. No resupply changes the meaning of a breakdown, because the timeline of repair changes with it. On Earth, maintenance is a logistics problem, but at 4 light years it becomes a design philosophy. You do not ask, can we fix it? You ask, can we fix it with what we already brought? The camera pans across a tool wall and each wrench looks suddenly like a survival ration. You cannot assume Earth can talk you through repairs in real time, because real time disappears with distance. Even at Proxima, radio delay is years, so troubleshooting becomes local, and mistakes become permanent. The crew's decisions will be made in silence, with only their own instruments as witnesses. A question sent home becomes a time capsule, and the answer returns to a different moment, to different people. That pushes the ship toward autonomy in software and in people, and autonomy has a cost. The crew must be technicians, medics, farmers, and governants, because specialists cannot be shipped in later. Every person must be cross-trained, and every skill must be practiced enough to survive stress. The camera watches a crew member rehearse a procedure in a cramped bay, repeating it until muscle memory replaces doubt. Spare parts become a second habitat, because they take volume, mass, and organization over decades. Every spare must be stored, tracked, protected from corrosion, and still fit decades later, even after design changes and wear. The camera moves through a storeroom of labelled crates, an archive of future emergencies. Dust motes drift in a flashlight beam, and the labels read like prophecies. There is also the slow danger of obsolescence, because a ship is frozen in time the day it departs. A connector standard that seems universal becomes rare, and a firmware tool becomes irreplaceable. The crew inherits not only equipment, but a technological era that cannot be updated from Earth. The ship becomes a museum that must still function, and the exhibits are bolted to life support. Some propose onboard manufacturing to reduce spares, and the idea is seductive in a closed world. Additive manufacturing helps, but it needs feedstock, calibration, and quality assurance that must also survive decades. A printer is not a magic box. It is another machine that can clog, drift, and fail. The camera shows a nozzle laying down a perfect line, then hesitating, then resuming with a flaw too small to see. A printed part that fails is not a warranty claim. It is a cascade that consumes time and confidence. The ship must verify its own repairs with metrology tools and conservative design margins, because you cannot test to destruction when destruction is lethal. Even measurement becomes a life support function. A caliper, a microscope, and a reference block become as essential as food, because they prevent invisible errors. Food is where closure becomes emotionally visible, because meals are routine and routine shapes morale. You can store calories for years, but decades demand stable nutrition, stable morale, and stable supply. The visuals linger on a galley table, simple, functional, and suddenly sacred. A spoon tapping a metal tray becomes a metronome for time, marking days that cannot be shortened. Stored food degrades in vitamins, fats, and texture, and the decline is slow enough to be ignored until it matters. Oxidation turns oils rancid, and some vitamins break down long before the calories disappear. Radiation and time change packaging and flavour, and appetite loss becomes a medical risk, not a preference. The camera shows a sealed pouch swelling slightly, then a hand hesitating before opening it, as if bracing for disappointment. When food becomes monotonous, the crew's psychology begins to fray around it. The same menu becomes a calendar, and the calendar becomes a reminder of how far there is to go. What does comfort mean when comfort must be manufactured, scheduled, and rationed? A birthday cake becomes a logistical event, and a shared meal becomes a form of governance. Regenerative agriculture promises renewal, but it imports complexity into every corner of the ship. Plants need light, water, CO2, nutrients, pollination, and disease control in a sealed environment. Each requirement is another loop to balance, and each loop can destabilize the others. The camera drifts through green racks under magenta LEDs, and the leaves look lush, yet the plumbing beneath them looks like a warning. Lighting is not just brightness, it is power and heat is always a problem in space. Every photon you grow becomes waste heat you must radiate, and radiators are mass and vulnerability. The camera cuts from glowing plant racks to the ship's exterior panels, thin, cold, and exposed. In the silence outside, those panels bleed warmth into darkness, and darkness is endless. Hydroponics and aeroponics reduce soil mass, but they increase plumbing and biofilm risk, and risk accumulates with time. Soil-based systems buffer chemistry, but they invite pests and unpredictable microbial shifts. Either way, the farm is not a hobby. It is a critical subsystem with failure modes. The camera shows roots suspended in mist, then cuts to a clogged sprayer head, crusted with minerals like scale on an old pipe. Pollination is a hidden dependency that looks trivial until it disappears. If you rely on insects, you must keep an insect ecosystem stable, and if you rely on humans, you add labor and error. A missed pollination cycle is not a missed harvest. It is a delayed recovery that can echo for months. The camera watches a gloved hand brush a flower, careful and repetitive, like a technician servicing a valve. Crop disease is not a farm problem, it is a mission problem, and the sealed environment makes it sharper. A fungus outbreak in a sealed habitat can take the food system down faster than you can redesign it. Spores ride air currents, cling to tools, and exploit every lapse in sanitation. Under a microscope, the spores look like stars, and the narrator lets the comparison hang. Beautiful, indifferent, and multiplying. Monoculture is efficient until it fails, and in a closed world, failure is not localized. Diversity increases resilience, but diversity increases management complexity, and complexity increases failure opportunities. The ship must choose a portfolio of crops the way an investor chooses assets, balancing yield, risk, and labor. The camera pans across trays of greens, legumes, and tubers, each labeled with growth cycles like a flight plan. Nutrient cycling is the hard part of closed loop, because atoms must be shepherded, not merely conserved. Nitrogen, phosphorus, potassium, and trace minerals must be recovered from waste without concentrating toxins, heavy metals, or persistent organic compounds. The farm must be fed, yet it must not be poisoned by its own recycling. The camera shows a clear solution turning faintly yellow in a test vial, and that colour becomes a decision. If a nutrient loop drifts, you do not notice immediately, and that delay is dangerous. You notice months later in plant stress, lower yields, and a slow tightening of ration margins. The visuals show leaves paling, growth slowing, and the crew measuring, adjusting, and hoping the next cycle recovers. A harvest bin that should be full is half full, and the empty space feels heavier than the food. This is why the ship must be a biosphere, not a pantry, and the distinction is brutal. It must maintain stable ecological feedbacks while also being a machine that accelerates, spins, and absorbs radiation. The habitat is alive in the sense that it is dynamic, and dynamic systems can oscillate. A stable-looking ecosystem can be one perturbation away from a swing, and the swing can arrive late. We have tried to build sealed biospheres on Earth, and the results are cautionary rather than triumphant. Sealed habitat trials showed CO2 swings, oxygen drift, and ecological surprises that defied planning. In the visuals, graphs crawl upward and downward like heartbeats, revealing instability where stability was promised. The camera finds condensation on glass walls, then the faces behind the glass, watching their own experiment breathe. Those experiments were not failures of effort, but demonstrations of complexity. A closed ecology contains many reservoirs: air, water, biomass, soil, microbes, and carbon moves between them on different timescales. When one reservoir lags, the system overshoots, and the correction arrives late. The crew becomes a moving variable because appetite changes, workload changes, and even sleep changes the chemistry. Small imbalances amplified through feedback loops because biology is non-linear and often delayed. Soil chemistry changed, microbial communities shifted, and human metabolism became part of the control system. When people breathe, sweat, and eat, they are not just passengers, they're actuators in the system. The camera follows exhaled vapor into a vent, then into a plant rack, then back into a glass of reclaimed water. Even when the habitat did not collapse, it demanded constant intervention, and intervention is its own cost. That is the uncomfortable lesson, because intervention is a form of resupply, just delivered as labor and attention. If the crew must constantly fight the system is not truly closed. The question becomes sharp and quiet. How much human vigilance can you budget for 40 years? The ISS is the opposite lesson, and it is equally important for understanding the trap. The ISS uses advanced life support, yet it survives through a steady stream of cargo, spares, and consumables. The station's success is real, but it is a success built on logistics. It is a triumph of scheduling, customs forms, and launch windows, mundane things that become heroic when they never fail. Filters, pumps, seals, and sensors are replaced on schedule, and the schedule is a quiet miracle. That schedule is a supply chain, and a supply chain is a lifeline that an interstellar ship cannot have. The camera shows a cargo craft approaching, then cuts to empty space where no craft will come. The silence after the cut feels like a door closing. In low Earth orbit, a failed unit can be swapped within weeks, and ground teams can analyze the failure in detail. At proxima distances, a failed unit is either repaired locally or it becomes the new baseline. The crew will learn to live with degraded performance, until degraded performance becomes unacceptable. The ship's history becomes a gradual narrowing, as margins are spent one small failure at a time. Time also attacks the human body, even when systems work and the attack is subtle at first. Microgravity deconditions bone, muscle, and cardiovascular function, and the losses accumulate with mission duration. The ship can be perfect, and the body can still fail. The camera shows a treadmill harness floating, then tightening, then pulling a runner down with elastic force that imitates weight but never quite becomes it. We have data from months and some from a year, and the trend is clear enough to be ominous. Without gravity loading, bones lose density, muscles weaken, and orthostatic tolerance collapses when astronauts return to Earth. The body is built for weight, and weightlessness is a slow unbuilding. Even the inner ear, tuned for gravity, must rewrite its assumptions, and that rewiring has costs. The deeper worry is not only strength, but repair. Bone is living tissue that remodels in response to stress, and without stress, the balance shifts toward loss. Over decades, that loss becomes fracture risk, dental issues, and a medical burden that compounds with age. A minor fall becomes a major event when the skeleton is quietly hollowed by time. Exercise helps, but exercise is a partial patch rather than a replacement for gravity. It consumes crew time, it wears equipment, and it does not fully replicate the constant loading of standing, walking, and lifting. Even the best protocols are a negotiation with physiology, not a victory. The camera shows a worn belt on a treadmill, then a spare belt in a crate, and the implication is plain. Radiation and microgravity interact with immune function and inflammation, and the interactions are still being mapped. Over decades, the risk profile shifts from acute injury to chronic decline, where small impairments accumulate into vulnerability. A minor infection can become a major event when immunity is altered. The ship's medical bay is not waiting for one dramatic trauma. It is waiting for the slow grind of probability. A 40-year mission also implies aging in flight, and aging changes everything about medical planning. The crew will not just travel through space, they will travel through middle age, frailty, and changing medical needs. The ship must carry not only tools, but the capacity for long-term care. The camera holds on a pill organizer, then on an ultrasound probe, then on a shelf of manuals that must outlast their authors. That is why artificial gravity is proposed, not as comfort but as risk reduction and system simplification. Rotation can provide centripetal acceleration that mimics gravity if the radius is large enough and the rotation rate is tolerable. In plain terms, you spin a habitat so the floor pushes back. The camera reveals a rotating ring in silhouette, slow enough to feel calm, yet relentless enough to never truly stop. A rotating habitat introduces engineering burdens that do not fade with time because rotation is relentless. Bearings, seals, structural fatigue, and vibration control must remain stable for decades, and small imbalances can grow into wobble. The visuals show a ring turning slowly, then a close-up of stressed joints and rotating couplers. A vibration sensor needle trembles, and that tremble becomes the first hint of a future repair. Small radius rotation creates Coriolis effects that can cause nausea and coordination issues, especially when people move their heads. Large radius rotation reduces those effects, but large radius increases mass and structural loads. The design is a compromise between human comfort and mechanical reality. The camera follows a tossed object curving oddly through the air, tracing the geometry of rotation in a way the body cannot ignore. Some designs split the ship into rotating and non-rotating sections, and the split is never free. That adds joints, transfer tunnels and failure points, and every interface is a leak path. A rotating seal is a promise that must be kept for decades, and decades are hard on promises. The camera lingers on the interface collar, polished and precise, then imagines it after 20 years of wear. Even with gravity, confinement remains, and confinement is not solved by engineering alone. The crew will live inside a finite volume with finite privacy, finite novelty, and finite escape from each other. The camera drifts down a narrow corridor, identical doors, identical lighting, identical days. A calendar on a wall becomes a quiet monument to repetition. Isolation psychology is not a footnote. It is a mission system with measurable consequences. Stress, depression, conflict, and burnout can produce errors that no redundancy can fully absorb. A ship can survive broken hardware yet fail because people stop trusting each other's judgment. The camera watches two crew members pass in a corridor, their silence louder than any alarm. The crew will also experience cultural drift, because culture is what humans do when no one is watching. Language, norms, and priorities shift when a group is sealed together long enough to become its own society. What begins as a mission becomes a lineage of habits, stories, and unspoken rules. The ship's rituals, mealtimes, maintenance rounds, celebrations, become the gravity that holds minds in place. Governance becomes engineering, because disputes must be resolved without external authority or timely arbitration. A mission needs rules for labour, resource allocation, discipline, and succession, and those rules must be clear before stress tests them. In a closed world, politics is not optional, it is infrastructure. The camera shows a meeting table with bolted chairs, and the bolts feel symbolic, as if the arguments must stay contained. The burden is not only interpersonal, it is existential, and it presses hardest during emergencies. The crew knows Earth cannot help in time, and that knowledge changes every emergency into a private apocalypse. When alarms sound, there is no rescue ship on the horizon, only the crew's own hands. The camera cuts to flashing lights reflected in a visor, then to a hand reaching for a manual already worn at the edges. Communication delay makes reassurance impossible, and it changes the emotional meaning of a message. Messages become historical artifacts, and advice arrives after the decision has already been made. The camera shows a recorded video from Earth, smiles preserved, arriving years late, like light from a vanished star. A laugh plays in a quiet cabin, and the sound feels both comforting and cruel. This isolation also changes accountability, because there is no external regulator in the moment. A crew that must improvise repairs and policy becomes both operator and regulator, and mistakes become part of the ship's history. The ship's log becomes a constitution written in emergency ink. The camera lingers on handwritten annotations in a digital system, as if the crew is leaving evidence for a future that may never read it. Training cannot be a pre-flight checklist, because a checklist assumes a short mission and a stable world. The ship must carry education systems so skills persist, because expertise decays and new problems appear. Manuals must be living documents, and learning must be scheduled like maintenance. The camera finds a small classroom corner where diagrams are sketched, erased, and sketched again under recycled air. The camera finds a quiet corner where lessons are recorded, hands sketching diagrams, voices practicing procedures, a library of failures turned into curriculum. Knowledge becomes a consumable that must be replenished, even when nothing physical arrives. What happens when the only teachers are the people already exhausted? The ship must protect competence the way it protects oxygen, because both can leak away unnoticed. If the mission includes children or a generational crew, the ship becomes a cradle and a prison at the same time. Then life support must also support development, schooling, and social stability, while also managing risk and limited space. The question becomes uncomfortable. What does consent mean when birth occurs in transit? The camera holds on a small sleeping birth, scaled for a child, and the image lands like a moral weight. Even without children, the crew must manage grief and loss, because time makes loss statistically likely. A death in a sealed habitat is not only tragedy, it is logistics, morale, and a shift in labour capacity. The camera holds on an empty workstation, tools neatly arranged, then cuts away before the silence becomes too loud. In a closed world, absence is not abstract. It changes the schedule, the workload, and the air of the room. Medical care must cover dentistry, surgery, mental health, and chronic disease, because decades contain everything. Pharmaceuticals expire, so the ship needs long-life storage or onboard synthesis, and both require strict control. A mislabeled vial is not a paperwork error, it is a potential fatality. The camera shows expiration dates marching forward, then a hand rewriting inventory, as if trying to negotiate with time. Onboard synthesis adds chemical plants and quality control adds sensors and standards. Standards require expertise that must be maintained, even as people age and rotate through roles. The ship becomes a small hospital, a small factory, and a small laboratory, running continuously, with no outside accreditation. The camera tracks along stainless tubing and cleanroom gloves, then returns to a human face, tired and focused, because the system is only as careful as its caretakers. Every added capability reduces one risk and adds another. Because complexity is a double-edged tool, the ship becomes a stack of trade-offs, and time makes every trade-off visible. The longer you fly, the more the edge cuts, and the more carefully you must handle it. The camera pulls back through layers of systems, revealing how many things must be right at once. This is the fragility of time, and it is the chapter's quiet villain. A system that can run for a year is not automatically a system that can run for 40, because wear, drift, and rare failures accumulate. The ship must be designed for the long middle, not the triumphant beginning. The middle is where attention fades, where novelty dies, and where maintenance becomes destiny. A mission plan must assume continuous maintenance, because maintenance is how closed worlds stay alive. Maintenance requires tools, spare materials, documentation, and a culture that treats inspection as survival. The camera shows gloved hands checking seals, logging readings, and tightening fasteners with ritual care. A torque wrench clicks, and the click feels like a heartbeat, small, regular, and necessary. Yet maintenance itself creates risk, and the risk is not theoretical. Opening panels introduces contamination, repairs introduce human error, and every intervention is a chance to break something else. In a closed habitat, even dust from a repair can migrate into filters and lungs. The camera shows a cloud of fine particles drifting in lamplight, then being pulled toward an intake like a tide. So the ship must be designed for maintainability from the start, not retrofitted after problems appear. Components must be accessible, modular, and diagnosable without specialized ground equipment. The crew must be able to isolate a subsystem, bypass it, and restore function without improvising miracles. The camera follows color-coded quick disconnects and labeled panels, and the labels feel like a language the ship must never forget. Software becomes another long-duration hazard, because code is a machine made of assumptions. Code ages as hardware changes, and bugs that are tolerable in year 1 can become fatal in year 20. The ship's control loops must be robust against edge cases that only appear after millions of cycles. A single timing error, repeated often enough, becomes a pattern, and patterns become failures. Cybersecurity becomes internal, not external, and the enemy is physics rather than malice. A corrupted control system could be caused by radiation bit flips, not hackers, and the effect is the same. Error-correcting memory, watchdog timers, and redundant computation become the digital equivalent of oxygen. The camera shows a stream of bits on a diagnostic display, then a sudden correction, then calm again, as if the ship just caught itself breathing wrong. The ship must also manage its own calibration, because sensors drift and drift turns control loops into guesswork. Metrology becomes a daily ritual, with reference standards protected like heirlooms. When a pressure sensor lies by a few percent, the ship can spend months correcting the wrong problem. The camera holds on a sealed reference cylinder, then on a crew member's careful hands, because precision is now a kind of faith. When you add everything up, the ship stops looking like a vehicle, and that realization is the reveal. It becomes an artificial ecology wrapped around an industrial plant, with humans as both inhabitants and caretakers. The camera pulls back from a sleeping crew member to the humming machinery behind the wall. In that hum is the real sound of interstellar travel, not engines, but continuity. That is the haunting proposition of this chapter, and it is not softened by ambition. An interstellar ship must be a self-sustaining biosphere, and we have never built one that can truly run alone for decades. We have built prototypes, and we have learned, but we have not crossed that threshold. The nearest star remains close on a map, yet distant in the language of reliability. We have built stations that survive by resupply, and we have built sealed habitats that survive by constant intervention. We have not built a closed world that survives by itself, with no outside hand steadying the system. The difference between supported and self-sustaining is the difference between possible and proven. The camera returns to the lone hull, and the loneliness now feels technical, not poetic. The nearest star is not only a propulsion problem, and this is the chapter's core turn. It is a continuity problem, where biology, psychology, and reliability must hold steady longer than most institutions. What human organization lasts 40 years without resupply, without replacement, and without outside correction? The ship must be not only engineered, but governed, trained, maintained, and emotionally inhabited. So the tension shifts again, because even a perfect biosphere is still exposed, and exposure is the price of space. If the ship is a world, space itself remains hostile, and the next threats do not negotiate. Outside the hull, the universe is not empty. It is energetic, particulate, and indifferent. The camera tilts from interior warmth to exterior black, and the boundary looks thin enough to be imaginary. The next chapter turns outward from the habitat walls toward what strikes and penetrates. Radiation and high-speed impacts do not care about human plans, and the universe collects its debt in silence. The camera holds on the hull, then fades into a star field that looks calm only because it is far away. Space looks empty from inside the hull, but emptiness is a disguise that only works at a human glance. Beyond the windows, the stars hold still, and the darkness seems calm, yet the real environment is radiation, dust, and time acting together. The central question tightens again, because survival is not a mood or a slogan, and optimism does not absorb particles. What would it truly take, by real physics and real engineering, to send humans to Proxima Centauri? And why does the nearest star still overwhelm us? In the early space age, we learned this lesson in short bursts, because missions were brief, and Earth was always close. Apollo crews crossed the Van Allen belts quickly, and even that passage was watched with anxious dosimeters and conservative timelines. The International Space Station lives under the umbrella of Earth's magnetosphere, where trapped particles and solar radiation are partly deflected and partly absorbed. That protection is not perfect, but it is a thick filter: air, magnetic field, and a planet's bulk between you and the storm. Interstellar flight removes that filter entirely, and the ship becomes its own tiny planet with no sky. Radiation is not a single threat, and it is not a single number that can be solved once. It is a spectrum of particles, energies, and arrival patterns that punish biology differently, and it also changes with solar cycles and cosmic history. In low Earth orbit, Earth's magnetic field and atmosphere absorb much of it, while the remaining flux arrives with familiar rhythms. In deep space, the shielding is whatever you bring, and whatever you can afford to accelerate for decades. If propulsion buys decades instead of centuries, radiation buys consequences instead of headlines. Start with the background that never turns off: galactic cosmic rays, the hiss beneath every other signal. GCR are high-energy nuclei, stripped atoms accelerated by supernova remnants and other violent sources, then scattered through the galaxy by magnetic turbulence. They travel near light speed, and their energies can be so high that a single particle carries the punch of a tiny, invisible bullet. They are not mostly protons like the solar wind, and that difference matters when the target is living tissue. Many are heavy ions, sometimes called HZE particles, with high charge and high energy that concentrate damage into narrow tracks. When an HZE ion passes through tissue, it does not merely hit a cell in the everyday sense. It leaves a dense track of ionization along its path, like a needle of chaos through water, breaking chemical bonds and tearing through DNA. Along that track, molecules become radicals, and radicals are chemically aggressive in plain language, because they steal electrons and destabilize nearby structures. The track structure matters because biology is not uniform material, and cells respond differently to clustered damage than to diffuse damage. A low dose spread gently over a wide area can be repaired, but clustered double-strand breaks can overwhelm repair pathways. That is why high linear energy transfer radiation can be biologically potent even when the dose rate seems modest. Dose is often measured in sieverts, but sieverts hide complexity behind a single unit. A sievert tries to weight physical energy deposition by biological effectiveness, yet the weighting factors are imperfect and still debated for deep space spectra. Two equal doses can produce different outcomes depending on particle type, energy, and where in the body the energy lands. Even the same particle can be more damaging if it traverses sensitive stem cell niches or the eye's lens epithelium. Radiation protection therefore becomes probabilistic engineering, designing for distributions, not certainties. The ship is built in the shadow of unknowns that cannot be tested at full scale on Earth. GCR are hard to shield because they are fast, penetrating, and indifferent to thickness in the way we wish they were not. A thick wall can stop some particles, but it also becomes a target, and targets create consequences. When a high-energy nucleus hits shielding, it can fragment into secondary radiation, a cascade of lighter particles that continue forward. That secondary shower can include neutrons, protons, and lighter ions that spread deeper into the habitat volume. So the shield is not only a barrier, it is also a particle factory, and the factory runs whenever the galaxy sends a visitor. This is the paradox that haunts every clean diagram of more shielding equals safer. Add mass and you may reduce the primary flux, yet you can also raise the internal complexity of the radiation field. Neutrons are especially troublesome because they are uncharged, so magnetic tricks do not steer them, and they can penetrate deeply before interacting. Secondary gamma rays can add another layer of exposure, and their paths are long and hard to predict. The crew can be protected from one spectrum while being exposed to another, and the difference is not visible until biology keeps the score. The second radiation source is intermittent, and it arrives like weather that turns lethal without warning. Solar particle events erupt from the sun during flares and coronal mass ejections when magnetic fields reconnect and fling charged particles outward. SPC radiation is often lower energy than GCR, but the flux can spike dramatically, and intensity matters as much as energy. A major event can deliver a dangerous dose in hours, not months, and it can saturate sensors and confuse diagnostics. The mission must assume the sun will eventually throw a storm at the ship, because over decades the odds stop being odds. The sun's behaviour is not static, and history reminds us that rare events still happen. The 1859 Carrington event lit telegraph wires on fire, and modern infrastructure fears its return. But astronauts would fear it for a simpler reason. In deep space, the storm is not a threat to power grids, but to blood-forming tissues, gastrointestinal lining, and the delicate machinery of the immune system. Even smaller historical events, inferred from ice cores and tree rings, hint that the sun can exceed our short modern memory. At proxima distances, there is no real-time warning from Earth that matters, because the light-speed delay turns advice into archaeology. The crew must detect, decide, and shelter using their own instruments and their own judgment. The ship, therefore, needs two kinds of protection that fight each other in mass and layout. It needs broad shielding for the constant drizzle of GCR over decades, because chronic exposure is a slow grind that never takes a day off. It also needs a storm shelter for the short, intense pulses of SPE exposure, because acute doses can end a mission quickly. A shelter can be small and heavily shielded because it protects people briefly, and brief protection can be concentrated. But the rest of the habitat still exists, and people still live there most days, working, sleeping, and exercising in spaces that cannot all be bunkers. The design becomes a geometry of risk, where time spent in each volume matters, and where the map of the ship becomes a medical chart. Corridors, workstations, sleeping quarters, and exercise rigs each carry a different radiation signature depending on nearby tanks, equipment, and structural ribs. Even orientation matters, because a forward-facing wall may see a different flux than a wall shadowed by propellant or cargo. Over years, the crew learns the ship the way sailors learn weather, except the weather is invisible and the consequences are delayed. You can imagine small colour maps on a display, greens and yellows shifting with solar activity, quietly advising where to linger and where to hurry. Time is the enemy because dose accumulates, and biology remembers in ways that are not negotiable. Radiation risk is partly deterministic at high doses, where certain injuries appear above certain levels, but deep space risk is often stochastic. Stochastic means probability rises with dose, even when no threshold is guaranteed, and that is a cruel kind of uncertainty. Cancer risk is the headline, but it is not the only outcome that matters, and it is not the only way a mission can fail. The mission is long enough that chronic effects become mission effects, not merely post-mission statistics. Over decades, ionizing radiation increases lifetime cancer probability in a way that is hard to personalize. because individuals do not share identical genetics or repair capacity. The body's repair enzymes work constantly, but they are not magical, and they make mistakes that accumulate like tiny transcription errors in a long book. A crew does not experience risk as a percentage, but as a future that becomes uncertain, and uncertainty changes behaviour. It changes how you plan, how you think about your own body, and how you interpret every ache that would be trivial on Earth. Radiation also increases cataract risk by damaging the eye's lens over time, because the lens has limited ability to repair itself. Cataracts are not dramatic, but vision loss in a closed world is operationally dangerous, and it arrives as a gradual blur that steals confidence. The crew needs sharp eyes for maintenance, navigation, and emergency response, and deep space operations are unforgiving to hesitation. A technician reading a micrometer, aligning a valve, or inspecting a hairline crack cannot afford a fogged lens or degraded contrast sensitivity. Even small visual deficits can lengthen repair times, and time is always a resource in a ship with limited redundancy. Medical intervention is also constrained, because surgery in microgravity is complex and supplies are finite. Even if you had the tools, you may not have the spare hands, the sterile field, or the margin for complications. The ship must treat prevention as the primary medicine, because cure is not guaranteed. The central nervous system is a deeper worry, because it is not easily repaired and not easily replaced. High-energy particles can cause neuroinflammation and microstructural damage in brain tissue, and the brain's wiring is more fragile than it looks. Some effects may be subtle: synaptic changes, altered neurotransmitter balance, or vascular stress that slowly erodes performance. Animal studies suggest cognitive and behavioral effects that scale with dose and particle type, including changes in memory, attention, and decision-making. Human data is limited because we have not kept people in deep space for decades, and we have never done it at interstellar cruise distances. So a Proxima cruise becomes a research program conducted on living brains, with no ethical escape hatch once the ship departs. The danger is not only intelligence in the abstract, but judgment under stress, because missions fail in moments. A small shift in impulse control, a slower reaction time, or a subtle change in mood can become a chain of operational mistakes. In a closed habitat, interpersonal conflict is not merely unpleasant, it is a systems risk that can degrade coordination and trust. Radiation is therefore not just a biomedical hazard, but a governance hazard, because it can change the crew that governance depends on. The ship must be designed for humans as they will be after years of exposure, not only as they are at launch. That design includes procedures, cross-training, and decision structures that tolerate a little cognitive drift without collapsing. Fertility and reproductive health add another layer of uncertainty and ethics, because biology does not pause for mission timelines. Radiation can damage germ cells and increase mutation risk in sperm and eggs, and mutations are not always obvious at first. It can also affect endocrine function and pregnancy outcomes in ways not fully mapped, especially across long exposures and mixed radiation fields. If the mission includes a multi-age crew, reproduction becomes a biological hazard question that collides with human rights and human longing. If the mission forbids reproduction, it becomes a governance and consent question that must be settled before departure, because there is no court in interstellar space. Even the decision to preserve fertility through cryostorage becomes a mass and power question, because every ethical option has an engineering footprint. Now connect the biology back to the calendar that propulsion created, because speed does not erase time, it reshapes it. At 0.1c, a one-way cruise is roughly 4 decades, before braking and margins are not optional when lives depend on them. Even if the ship is fast, the exposure window is still measured in human aging, with birthdays passing under artificial lights. A short mission can accept higher dose rates with limited cumulative harm, because the body's repair systems can keep up for a while. A long mission turns moderate dose into a lifetime burden carried inside the hull, and the burden does not vanish at arrival. The destination does not reset the clock. Your cells arrive carrying every year of the crossing. The crew's baseline health becomes part of the propulsion equation, because the ship is only as capable as the people maintaining it. A design that requires constant EVA, constant repairs, or constant high cognitive load operations becomes less viable as radiation slowly erodes performance. That erosion is not a dramatic collapse, but a gradual narrowing of safe operating margins. The mission plan must assume that some tasks will become harder, slower, and riskier with time. Interstellar engineering therefore becomes interstellar medicine, whether we admit it or not. The medical bay is not an accessory, it is a control room for the human machine. Passive shielding sounds simple, because it is the oldest idea in engineering, and it fits the intuition of walls and armour. Put mass between people and radiation, then accept the mass penalty, and in a short mission that can be a reasonable trade. But the mass penalty is not a footnote in interstellar flight, where every kilogram must be accelerated to a fraction of light speed. Every kilogram of shielding must be accelerated, cooled, protected, and possibly decelerated, and each of those verbs implies additional systems. Shielding therefore competes directly with propulsion, radiators, spares, and habitat volume, and the competition is ruthless. You do not just add a wall, you add a chain of consequences that follows the wall through the entire design. Material choice matters because radiation interacts with nuclei, not with intentions or marketing claims. Hydrogen-rich materials tend to be effective per unit mass for some radiation types, especially for slowing charged particles with fewer secondary fragments than heavy metals produce. That is why water, polyethylene, and other light element materials are often proposed, and why the language of shielding often sounds like the language of chemistry. Hydrogen's single proton is a gentle collision partner, which is plain language for fewer violent nuclear breakups. Water is especially tempting because it can serve as both shielding and life support reserve, and it is already a necessity for humans. In a well-designed ship, necessities can be arranged to do double duty, and double duty is how you survive mass budgets. A common concept is a water wall around crew quarters, or a central storm shelter wrapped in tanks and supplies. Water can be stored in tanks arranged to create a protective shell, and the shell can be thickest where people sleep because sleep is long and immobile. Visualize it as a quiet circular room at the ship's center, with translucent tanks forming a ring, an aquarium of survival. In an emergency, the crew moves inward, straps down, and listens to particle counters tick like distant rain. But water is heavy, and heavy becomes punishing when you need many tons, especially when the mission already carries life support reserves. If you concentrate it in one place, you protect one region and leave others exposed, and exposure elsewhere still counts. If you distribute it everywhere, you increase plumbing complexity and leak risk, and leaks in a closed habitat are never trivial. Water lines must tolerate thermal cycling, vibration, and micrometeoroid damage, and each joint becomes a potential failure point. Contamination also becomes a concern because shielding water may not be pristine drinking water without treatment. The ship therefore needs careful segregation and filtration, and those systems add more mass and more maintenance. The simple idea of use water becomes a network of engineering decisions that must remain stable for decades. And decades are long enough for small leaks, small biofilms, and small corrosion sites to become large problems. Dense shielding like lead feels intuitive, because humans have used dense materials as protection for generations. In hospitals, lead aprons and thick walls are familiar, and the association is powerful, but intuition fails at high energies. High Z materials can generate more secondary radiation when struck by GCR, because heavy nuclei offer more ways to fragment incoming particles. They can also create Bremsstrahlung X-rays from electrons, adding another component that penetrates and spreads. So the best shield is not necessarily the densest and not necessarily the thickest, and the word armour becomes misleading. The ship does not need medieval plate. It needs a carefully tuned filter for a spectrum that does not care about human metaphors. The best shield is often layered, tuned, and still imperfect, because perfection would require impossible mass. Layering becomes a design language for both radiation and dust, and the language has grammar, low Z outer layers to slow particles, inner layers to absorb secondaries, and structural layers to hold everything together. But each layer adds mass, and each interface adds structural complexity, and complexity is the seed of failure. The ship becomes a stack of compromises where every improvement has a cost elsewhere. This is the same mass cascade seen in propulsion and life support, now weaponized by physics. The question is never, can we shield? But what do we give up to shield, and what risks do we accept instead? Active shielding is the idea that tries to escape mass by using fields, and it carries the seduction of science fiction. Instead of stopping particles with matter, you deflect charged particles with magnetism, turning the ship into a small artificial magnetosphere. A magnetic field can bend trajectories, reducing the flux that reaches the habitat, and in principle, it could be adjusted as conditions change. An electric field could also repel or steer charged particles in principle, although maintaining large potentials in plasma is difficult. Active shielding is appealing because it sounds like a weightless umbrella, and umbrellas are what humans reach for in storms. The visual is irresistible, glowing field lines arcing around the hull like an invisible cage. The problem is scale, because space radiation is not a lab beam with tidy energies and controlled angles. To meaningfully deflect high-energy ions, you need large field volumes and strong fields, and the field must extend far enough that particles are turned away before they intersect the habitat. Strong fields imply superconducting coils, cryogenic systems, and structural supports that resist magnetic forces trying to tear the coils apart. Those supports must survive decades of vibration, radiation, and thermal cycling, and they must do it without constant human intervention. The shield becomes a major spacecraft subsystem, not a gadget bolted on late, and every subsystem you add becomes another thing that can fail far from help. Power is another constraint that refuses to stay small, because interstellar ships are always power limited in practical terms. Superconductors reduce resistive losses, but cryocoolers still need continuous power, and continuous power implies continuous heat that must be rejected. Quenches and faults must be managed safely because stored magnetic energy can be enormous, and the release can be violent. A failure could dump heat, damage coils, and create a cascading loss of protection at the worst possible time. Active shielding therefore trades mass for complexity, and complexity for reliability risk, and reliability is the currency you cannot borrow. The crew would live inside a system that must stay stable not for minutes, but for decades. Active shielding also has uncertain biological side effects, and uncertainty is not a small thing when exposure lasts decades. Strong magnetic fields near habitats raise questions about long-term human exposure, including vestibular effects and interactions with medical devices or implants. They also interact with plasma, charged dust, and spacecraft systems in complicated ways, potentially creating currents and forces where you do not want them. A field that protects from one direction may funnel particles into another region, because fields guide as well as repel. So active shielding remains conceptually attractive and operationally unproven at full scale, and unproven is a dangerous adjective in interstellar planning. The ship cannot be a prototype when the nearest repair shop is 4 light-years away. Even if radiation was solved, relativistic travel adds a new source of damage that feels almost unfair. At high cruise speed, the interstellar medium stops being a gentle background and becomes an oncoming stream with lethal energy. Hydrogen atoms become incoming projectiles with kinetic energies set by your velocity, and at fractions of c those energies reach into regimes we associate with particle accelerators. Dust grains become hypervelocity bullets, and the ship cannot dodge them reliably, because the distances are too large and the reaction times are too small. Speed is protection against time, but it is also a multiplier of impact energy. The faster you go, the more the universe hardens in front of you. Interstellar space contains gas and dust at low density, but the path length is enormous, and enormous distances turn small probabilities into expectations. Over light years, even sparse dust becomes an expected number of impacts. An expectation is not comfort. At fractions of c, a microscopic grain carries energy comparable to a small explosive, concentrated into a point smaller than a pinhead. The danger is not only puncture, but the spray of plasma and fragments created on impact, because impact energy becomes heat, ionization, and shock. Those fragments can become secondary radiation and secondary shrapnel inside the shield, adding insult to injury. In visual terms, each impact is a brief, silent flash, an invisible firework that the hull must survive again and again. This is where shielding becomes a double-duty structure with conflicting requirements, and the conflict is not philosophical, it is mechanical. A forward shield must absorb impacts and manage heat and debris without failing, which suggests toughness, thickness, and sacrificial design. A radiation shield must minimize secondary particle production and protect biology, which suggests light elements and careful layering. A structure optimized for one may be poor for the other, and the ship cannot afford 2 separate noses. The ship's nose becomes a sacrificial system designed to be damaged on purpose, and that is a strange thing to accept when humans live behind it. What does it do to morale, knowing your first line of defense is meant to erode like a candle? Whipple shielding is one of the most practical approaches we know, because it uses geometry rather than brute strength. A thin bumper layer breaks an incoming particle, into a cloud of fragments, converting one concentrated impact into many smaller ones. A standoff distance allows that cloud to spread before hitting a rear wall, and spreading reduces peak stress. The rear wall then absorbs the dispersed energy over a larger area, and the structure survives what would otherwise be a puncture. This works for micrometeoroids at orbital speeds, but interstellar speeds are harsher, and the fragment cloud can be hotter and more ionized. The standoff gap becomes a violent mixing zone, full of expanding plasma that must not reach the habitat. At higher fractions of C, the standoff distances and layer thicknesses must grow, because the energy scales with velocity squared, and the scaling is merciless. That growth adds mass, and mass adds propulsion cost, and propulsion cost adds heat rejection, and heat rejection adds radiator area and vulnerability. The same coupling returns, because interstellar design is always a coupled problem, and every subsystem drags the others with it. If you add 10 tons of forward shielding, you may add more than 10 tons overall, because you must support it, steer it, and keep it stable. You add structure to hold it, power to move it, and radiators to cool the power, and the ship grows like a living thing. Some concepts propose electromagnetic dust deflection ahead of the ship, a kind of invisible bull wave. Charge the incoming dust or create a plasma sheath that steers particles away, and you reduce the number of direct impacts on the hull. In theory, fields could reduce the number of direct impacts, and even a modest reduction could matter over decades. In practice, dust charging is variable, and neutral grains do not respond easily, and the interstellar medium is not uniform. A system that works sometimes is not enough when the mission lasts decades, because the one failure can be the one that matters. The crew cannot bet their lives on usually, because the universe only needs one exception. Forward shielding also cannot be a single plate, because impacts will erode it, and erosion is cumulative. The design must assume gradual ablation and include margin for loss over time, like a heat shield that never stops re-entering. That means thicker shields, replaceable layers, or consumable sacrificial mass that can be fed forward as protection. Consumable mass is still mass you must accelerate for the entire journey, even if you plan to spend it slowly. So the ship carries its own future damage as a payload, and the payload is a reminder that the universe is not passive. The hull is not just structure, it is a calendar, counting impacts you have not yet seen. Radiation and dust do not only threaten bodies, they threaten the ship's mind, the electronics that interpret sensors and execute decisions. Electronics face single-event upsets when energetic particles flip bits in memory, and the flip can be as small as a single corrupted instruction. A bit flip can be corrected, but repeated upsets can overwhelm systems and confuse diagnostics, especially if multiple subsystems are affected at once. Single-event latch-up can cause destructive currents that permanently damage components, turning a transient into a hardware loss. Long missions turn rare glitches into expected maintenance, and expected maintenance is a burden when spare parts are finite. The ship must behave like a data center that cannot reboot casually, because rebooting may interrupt life support. Radiation also causes total ionizing dose effects that slowly degrade semiconductors, and slow degradation is difficult to detect until it matters. Threshold voltages shift, leakage currents rise, and timing margins shrink, and the system becomes less tolerant of temperature swings and noise. A system that passes tests at launch can become unstable years later, not because of one dramatic hit, but because of accumulated microscopic changes. This is not a dramatic failure, but a drift into unreliability, and drift is dangerous because it hides. In a ship that must be autonomous, unreliability is a life support threat, because autonomy is not optional at light-year distances. Materials degrade too, and the degradation is quiet until it is structural, and then it is sudden. Radiation can embrittle polymers, darken optics, and weaken composites over time, and those changes can alter seals, insulation, and mechanical tolerances. Neutrons and high-energy ions displace atoms, creating defects and swelling in metals, and swelling can change clearances in bearings and joints. Thermal cycling adds fatigue, and micro-impacts add crack initiation sites, and the cracks wait patiently. Decades of exposure create a new material, one you did not test on Earth, because Earth cannot reproduce the exact spectrum and duration easily. The ship becomes its own long experiment in materials science, with the crew living inside the results. Optical sensors and star trackers can be blinded by radiation noise and damaged by dose, and guidance depends on those eyes. Solar arrays can lose efficiency as particles damage their crystal structure, and power margins shrink without drama. Insulation can become brittle, then shed particles that contaminate filters and mechanisms, and contamination is a slow killer of reliability. Every subsystem becomes a radiation story, not only the crew module, and the ship becomes an ecosystem of vulnerabilities. The ship's reliability budget is spent in invisible increments, and the crew may only notice when a margin is gone. By then, the question is not what failed, but what else is close behind. Now the intimate danger becomes clear, because the crew cannot step outside it, and they cannot take a break from the environment. They cannot rotate out of exposure, and they cannot be replaced by a rescue mission, because rescue would require another interstellar ship. Every day adds a small biological cost, and small costs compound into outcomes, even when each day feels normal. The voyage becomes a slow, cumulative assault that the body records in DNA, in proteins, in tissues that age faster than they should. The ship is not only travelling through space, it is travelling through a dose curve, and the curve is always rising. This is where the nearest star stops feeling like a destination and becomes a trial that tests the definition of crew. A 4-decade cruise at high speed is not only logistics and engineering, and it is not only a matter of keeping air breathable. It is a biological experiment conducted without a control group and without a recall, because you cannot undo the exposure. The test subject is human tissue, and the independent variable is time in deep space, measured in heartbeats and sleep cycles. The results arrive as probabilities, and probabilities still kill real people, because a probability becomes a person when the dice land. So the stakes rise again, because the mission cannot hide behind averages, and it cannot hide behind the language of acceptable risk. One crew member's cancer is not an acceptable rounding error in a closed habitat, because that crew member is also a specialist and a friend. One cataract that impairs a critical technician is not a minor medical note, because the ship is a machine that requires human hands. One cognitive decline that shifts judgment can become a chain of operational mistakes, because interstellar systems are complex and failure cascades are real. The mission plan must treat biology as a primary system, not a passenger, because the passenger is also the pilot. The grim realization is not that shielding is impossible, but that it is expensive in every currency that matters. It costs mass, which costs energy, which costs heat rejection, which costs area and vulnerability, and each cost echoes into another subsystem. It costs complexity, which costs reliability, which costs crew time and attention, and crew time is the one resource that cannot be manufactured. It costs uncertainty, because deep space radiation biology is still partly unknown, and unknowns do not negotiate with schedules. The ship becomes a compromise between what physics demands and what humans can endure. And compromise is not a comforting word when stakes are absolute. This returns us to the hook, because Proxima is close only on a map, and maps lie by omission. Every honest calculation turns that short trip into a sentence longer than a human lifetime, even when the ship is fast by any historical standard. The sentence is written not only in propellant and power, but in accumulated damage, in microfractures and mutated cells. Closest is a trick of perspective when the path is an ocean of vulnerability, and oceans do not care how brave you feel. And vulnerability is the one resource a crew cannot resupply, because you cannot order new DNA or new eyes. If humans are too fragile for the crossing, the mission architecture must change, and the change is not sentimental. We may need to send something else first, something lighter, faster, and less breakable, because physics rewards what can endure extremes. Machines can be hardened, replicated, and accepted as expendable in ways humans cannot, and they do not require a living habitat with medical ethics. A probe can take risks a crew cannot, and it can fail without turning tragedy into a tomb. So the story pivots toward precursors, probes, and the logic of sending minds without bodies, because information can travel where flesh cannot yet follow. The next chapter asks what we should send when we cannot yet send ourselves. Proxima Centauri sits close on a star chart, yet it still defeats our timelines, because distance is patient and biology is not. Chapter 5 ended with bodies and hulls losing the fight against space itself, where mass becomes liability and time becomes the final predator. So we pivot to the lightest thing we can send, and the fastest push we can imagine. Not a crude arc, not a fusion cathedral, but a wafer and a sail. Laser sailing begins with a quiet fact that feels like a trick. Light carries momentum, even though it has no rest mass. In everyday life, photons seem weightless, but in physics they still carry energy, and energy has inertia in motion. Momentum for light is energy divided by the speed of light, which means every watt is a tiny continuous shove. When photons reflect, they transfer twice the momentum they would by absorption, because the direction reverses and the change is larger. The force is tiny, but it never stops if the beam never stops, and that persistence is the first spell. In the visuals, it is almost disappointing at first. A dark vacuum, a thin sheet like a glint of frost, and a beam that looks like nothing until it strikes and blooms. Yet in the numbers, the effect is real. Radiation pressure is measurable, and it has been measured again and again since the early 20th century. Solar sails have already ridden sunlight in our own system, where the pressure is weak but constant, and the trajectory slowly bends like a long exhale. That is the first seduction of a laser sail. You do not carry propellant, so you do not pay the rocket equation's exponential tax, where every extra meter per second demands more fuel, which demands more fuel to carry the fuel. You separate the energy source from the vehicle, and you leave the heavy power plant at home, anchored to Earth or orbit. The craft becomes almost nothing, because mass is the enemy of acceleration, and acceleration is the only way to make interstellar time feel human. A sail mission is an accounting problem in reverse, and the ledger looks unfamiliar. Instead of hauling fuel, you build a beam that does the hauling, and you accept that the infrastructure stays behind like a launch cathedral. Instead of a tank, you carry reflectivity and geometry, because the sail is both engine and nozzle. Instead of an engine bell, you carry a sheet that must stay perfect while being hit by a star, and perfection here means atoms behaving. In principle, the performance leap is staggering, and it is not a small upgrade from chemical rockets. A gram-scale probe pushed by a multi-gigawatt to terawatt-class laser could reach about 0.1 to 0.2 C, depending on sail area, reflectivity, and beam quality. That is 30 to 60,000 kilometers per second, a speed that makes our fastest probes look parked, as if they were drifting in syrup. In that regime, Newton still rules, but the margins become cruel, and tiny errors become destiny. Voyager 1 drifts outward at roughly 17 kilometers per second, a triumph that becomes a sentence of 70 millennia to Proxima, even if nothing breaks. Parker Solar Probe has touched about 190 kilometers per second, and even that implies thousands of years, because the distance is not a metaphor. Laser sails propose decades, not ages, by refusing to carry their own momentum source, and by compressing the acceleration into a short, violent burst. The story becomes modern here, because this is not a lone paper in a journal, forgotten in a library stack. Breakthrough Starshot announced a concrete goal in 2016, framed as a program rather than a daydream, and it landed with the weight of a dare. It aimed to send gram-scale star chips to Alpha Centauri within a human lifetime, using a ground or near-Earth laser array. The name was optimistic, but the underlying move was sober. Shrink the spacecraft until it can be thrown by light. The plan was brutally minimalist, and the minimalism was the point. A tiny payload would carry cameras, sensors, a clock, and a communication laser, all folded into a wafer that resembles a piece of black glass. A thin sail would catch the beam, accelerate for minutes, then coast for years, silent and cold. The mission would accept a flyby, because stopping was not part of the baseline, and the baseline was already a cliff. For a moment it felt like the first honest interstellar program, because it did not pretend the distance was negotiable. It did not ask for exotic physics, only extreme engineering, and engineering is at least something we can test. It did not promise humans, only data, and data is the currency of science. It did not hide the distance, it tried to outrun it, and that bluntness was refreshing. But laser sailing is a chain of requirements where each link is a cliff, and the drop is always waiting. The beam must be powerful enough to accelerate quickly, because you cannot keep a tight beam forever, no matter how perfect the optics. Diffraction spreads any beam with distance, because waves do what waves do, and spread turns force into waste. So the acceleration must happen close to Earth, while the beam is still concentrated, before the spot grows larger than the sail. In the mind's eye, you can picture the beam as a luminous spear, but physics insists it is a cone that slowly opens. Even with a huge aperture, the divergence is set by wavelength and diameter, and the math is indifferent to ambition. A longer wavelength spreads more, which argues for shorter wavelengths. But shorter wavelengths can be harder on materials and optics. Every choice trades one problem for another, and the mission is built from those trades. That pushes the concept toward an immense phased array, because one laser is not enough, and one mirror is never big enough. Many lasers must act like one coherent aperture, with phase control across kilometers, so their peaks and troughs align like synchronized swimmers. The array must steer the beam without moving a single mirror, by shifting phases in real time, because mechanical motion is too slow and too sloppy. It must also survive heat, weather, and the politics of building a planetary-scale instrument, where every neighbour sees a different risk. The visuals here are architectural and slightly ominous. A desert plateau, a grid of emitters stretching to the horizon, each one a bright eye that must blink in perfect unison. Cables and cooling lines run like veins, and the air above shimmers with waste heat, even before the beam fires. When it does fire, the array does not roar, but the atmosphere above it seems to tighten, as if the sky itself is being held. Power is the next wall, because momentum transfer is expensive, and the bill is paid in watts. To push a gramcraft to a fifth of light speed in minutes, you need power comparable to a major grid, delivered not as a steady trickle, but as a controlled surge. You need storage, switching, and optics that tolerate peak loads without distortion, because a slight warp becomes a miss. You need a facility that behaves like a weapon, even if it is built for exploration, and that dual-use shadow never goes away. There is also the uncomfortable arithmetic of efficiency. If the sail reflects almost perfectly, you waste less energy as heat, but you still must generate the beam in the first place. If the lasers are, say, tens of % efficient, the rest becomes heat in the array, and heat must be moved. Cooling towers, radiators, or heat pipes become part of the interstellar story, because thermodynamics is always invited. Sighting becomes a fight between physics and atmosphere, and the atmosphere rarely compromises. Ground-based lasers must punch through turbulence, water vapor, and absorption lines, and the air is never perfectly still. Adaptive optics can correct some distortion, but correction must be perfect on a target that is meters wide, accelerating away like a fleeing insect. Space-based arrays avoid air, but they create a launch and assembly problem that rivals any mega-project, and they must survive micrometeoroids and radiation for years. On screen, the difference is stark. On Earth, you see a beam struggling through shimmering air, the way starlight twinkles because the atmosphere is restless. In space, you see a clean, hard line, but the structure that makes it is fragile, a lattice of panels and emitters that must hold alignment across temperature swings. Either way, the beam is not just light, it is infrastructure made visible. Even if you build the array, you must keep the beam on the sail, and that is not a casual tracking problem. The sail is tiny, accelerating at thousands of G, and it is trying to run away faster every second. A micro-radian pointing error becomes a miss measured in kilometers at long range, and the range grows quickly. The beam must track a target that is both moving fast and trying not to tumble, and it must do so while the Earth rotates and the platform flexes. Phased arrays can steer quickly, yet they also amplify small errors, because coherence is unforgiving. Phase noise widens the effective beam and reduces intensity where it matters, like a flashlight that refuses to focus. Thermal gradients warp optics and change phase, and the system must correct itself while delivering impossible power. The beam is not just bright, it must be exquisitely shaped, with a profile that stabilizes rather than destabilizes the sail. That shaping matters because the sail is not a rigid dish, and it cannot behave like one. If the center is pushed harder than the edges, the sail can cup, and a cupped sail can act like a lens, bending the beam in ways you did not intend. If the edges are pushed harder, it can flip like a coin in a gust, and the beam is lost. The control problem is embedded in the physics of the sheet, not added later with software. The sail itself is the most fragile part of the dream, and it is where the dream becomes a materials thesis. It must be extremely reflective to minimize heating, because absorbed light becomes temperature, and temperature becomes failure. It must be extremely light to maximize acceleration, because every milligram steals speed or demands more beam power. It must also be extremely stable, because instability turns thrust into spin, and spin turns a sail into confetti. At the flux levels required, the sail faces an environment like re-entry, but without air to carry heat away, and without the thick heat shield we rely on. Any absorbed fraction becomes heat that must radiate from a surface measured in microns, and radiative cooling scales with temperature in a steep way. If reflectivity drops by a tiny amount, temperature rises sharply and the margin disappears. A small defect becomes a hotspot, and a hotspot becomes a tear, and a tear becomes a mission that never leaves the solar system. In a close-up visual, the sail looks like a soap film stretched over darkness, trembling with invisible pressure. Under the beam, it glows faintly, not because it is supposed to, but because nothing is perfectly reflective. Tiny ripples travel across it like waves on a pond, and each ripple is a potential instability. The camera lingers on a microscopic flaw, and you can almost feel the heat concentrating there. Material science becomes the mission, not a supporting detail, because the sail is both structure and engine. Candidate films must survive high photon pressure without wrinkling, and the pressure is small per square meter, but relentless at extreme intensity. They must resist ablation, ionization, and micro-cracking under extreme acceleration, where internal stresses rise faster than intuition expects. They must be manufactured with near-perfect uniformity, because thickness variation changes force distribution, and uneven force becomes torque. The words get technical because the problem is technical. Reflectivity depends on refractive index, surface roughness, and coating design, and the best solutions may be multi-layer stacks tuned to a specific wavelength. But multi-layers can delaminate under heat, and they can introduce absorption bands that become lethal under terawatt illumination. Even the choice of wavelength becomes a design constraint, because optics, atmosphere, and sail coatings all prefer different answers. The sail also has to behave like a controlled mirror, and mirrors are picky. If the beam hits off-center, torque builds, and torque means the sail begins to rotate, which changes the angle, which changes the force. If the sail is not perfectly flat, it can act like a lens and self-defocus the beam, reducing thrust at the worst moment. If it is too flexible, it can flutter, and flutter can couple into catastrophic modes, where a gentle oscillation becomes a runaway tear. Designers propose metasurfaces and engineered patterns to stabilize the sail, and this is where modern nanofabrication enters the narrative. A patterned reflectivity can create restoring forces that self-center the beam, like a ball rolling back into a bowl. In theory, the sail becomes its own attitude control system, with no moving parts and no propellant. In practice, that means nanofabrication at scale, with tolerances that must survive launch and acceleration, and that must remain stable under heating. Then there is the payload, the chip that makes the sail worth building, and it is a cruelly small box. A gram-scale probe cannot carry much shielding, much power, or much redundancy, which means single points of failure are everywhere. It must survive the launch environment, the acceleration shock, and years of radiation exposure, including cosmic rays that flip bits and slowly degrade semiconductors. It must also remain functional after the beam phase, when it becomes a drifting speck, powered by something tiny and long-lived. Miniaturization helps, but it does not erase physics. Cameras need apertures, and apertures need area, and area adds mass. Sensors need calibration, and calibration drifts with temperature and radiation. Even a clock becomes a problem, because timing errors accumulate, and timing is navigation when you're alone between stars. Navigation sounds simple until you write the numbers, and the numbers are merciless. You're aiming at Proxima across 4.24 light-years, which is about 40 trillion kilometers, and the line between success and empty space is thin. Any initial velocity error becomes a misdistance that grows for years, like a hairline crack that becomes a fracture. Tiny angular errors at departure become astronomical offsets at arrival, because small angles multiplied by huge distances become huge mistakes. A probe can correct its course, but correction requires propulsion, and propulsion requires mass, which laser sailing refuses to carry. So the craft must rely on minimal cold gas, photon thrusters, or clever sail trimming, and each option has limited authority. Cold gas demands a tank, even if it is microscopic, and tanks are heavy relative to a gram. Photon thrusters are elegant, but the thrust is tiny, and time is limited. That means autonomy that can sense drift and correct without ground control, and autonomy here is not a luxury feature. Autonomy is forced by physics, because communication is delayed by years, and a probe cannot ask Earth what to do when it sees a problem. It must detect, decide, and act with limited sensors and limited computation, while its power budget is measured in whispers. That is the same autonomy theme from the crewed ship compressed into silicon and stripped of second chances. Targeting also includes a darker problem because Proxima is not a quiet sun. Proxima is a flare star and its space weather is violent, with bursts of radiation that can spike without warning. The probe must approach a system where radiation spikes and plasma conditions vary, and those variations matter at high speed. A tiny craft has little protection against a storm that can saturate detectors, charge surfaces and damage electronics, all while it is trying to take its only pictures. Even if the probe arrives on target, arrive is not the same as learn, and this is where the story tightens. Data return is the quiet killer of tiny probes, because information has to climb back across the same abyss. A Gram craft has a tiny antenna aperture and tiny electrical power, and both are enemies of a strong signal. Over light years, signal spreads as the square of distance, and the link budget collapses into near zero. Radio transmission from a Gram probe is almost hopeless at useful data rates, and it is not because radio is old-fashioned. The transmitter power would be milliwatts, the antenna gain would be small, and Earth would see a whisper under cosmic noise, competing with the background of the galaxy. You can integrate signals for long periods, stacking faint photons into meaning, but a flyby does not give you long periods. The probe is in the interesting region only briefly, and then it is gone. So Starshot and similar concepts lean toward laser communication, because lasers can form narrow beams, and narrow beams waste less energy. A small onboard laser could send a tight signal back to Earth, and in principle, that makes the math less hopeless. A narrow beam reduces spreading loss, but it demands extreme pointing accuracy, and pointing is the recurring nightmare of this chapter. The probe must aim a pencil-thin signal at a moving Earth, years after launch, while Earth itself orbits the Sun and spins. Pointing accuracy becomes a recursion of the original problem, like a riddle that answers itself with another riddle. The craft must know its attitude precisely, stabilize itself, and keep a laser locked on a target smaller than a pixel in its sky. It must do this while spinning, vibrating, and being pushed by tiny disturbances, including photon pressure from starlight and impacts from dust. A single misalignment can turn the return signal into nothing, and nothing is the most likely outcome. Earth, meanwhile, must listen with an instrument as ambitious as the launcher, because the receiver is half the mission. You need large receiving telescopes, low noise detectors, and long integration times, and you need them coordinated across nights and seasons. You also need to know when the signal arrives, because the probe's clock can drift, and drift becomes uncertainty. The mission becomes a choreography across years, with no rehearsal, and with no way to tap the dancer on the shoulder. This is why getting there is not the same as doing science, and it is why speed is not automatically knowledge. A flyby at 0.2 C gives you minutes to hours in the target system, depending on what you count as close. Your camera exposures must be short, your pointing must be perfect, and your storage must not fail under radiation. Then you must transmit everything home with a power budget that barely exists, and with a beam that must not miss. In the imagined footage, the probe's view is a frantic rush. A red star swells from a bright point to a disk, and any planets are flashes of changing light and shadow. The habitable zone is not a place you enter. It is a ring you slice through, and the slicing is fast. The probe's sensors must decide what matters, because there is no time to take everything. And then comes the trap that makes the chapter a climax. At 0.2 C, the probe is not a visitor, it is a bullet. Interstellar space is not empty, and even sparse dust becomes dangerous when you hit it at relativistic speed. A grain the size of smoke can carry the energy of a projectile, and the probe has almost no shielding. The same speed that makes the trip possible also makes the environment violent. It crosses the habitable zone in a blink and it cannot brake, because braking requires momentum exchange with something, and there is nothing to push against. The deceleration wall is the price of speed, and it is not a footnote. A laser sail can accelerate by riding a beam from home, where your infrastructure lives. It cannot easily decelerate at destination, because there is no destination beam waiting, and building one would be a second interstellar program. A flyby is the default outcome, because stopping is a different mission, with different physics and different mass. Speculative braking options exist, but each carries severe constraints, and each one steals from the simplicity that made Starshot plausible. A magnetic sail could use a large loop to interact with the interstellar medium, pushing against charged particles with a magnetic field. At relativistic speeds, the required loop size and field strength become enormous, and the forces can be destabilizing. The mass and deployment complexity can erase the advantage of being gram-scale, and deployment itself becomes a failure mode. Another idea is to use the target star's photon pressure, which sounds poetic and symmetrical. You could angle the sail to reflect starlight and bleed speed, turning the sail into a brake rather than an engine. But Proxima is dim compared to the Sun, and its radiation pressure is weak, especially far from the star. To brake significantly, you need a huge sail area and long interaction time, and long interaction time requires arriving with the right geometry. You can also imagine using stellar wind, or a close stellar pass for braking, diving deep into a flare star's environment. That means threading a needle near a star that throws tantrums, where plasma and radiation are hostile and unpredictable. It also demands navigation precision that a gramcraft struggles to achieve, because a small miss can mean no braking at all. Braking becomes a high-risk gamble, not a baseline plan, and the baseline is what programs are built on. Some proposals chain maneuvers, using Alpha Centauri A and B for gravitational and photon braking, then bending toward Proxima, and the elegance is real. Those trajectories are beautiful on paper, where gravity is smooth and timing is exact, and where sails never tear. They require arriving at the right place and time with tiny error margins, because the window for a gravity assist is narrow at high speed. They also extend mission duration, which fights the original promise, and they add complexity that multiplies failure modes. So Starshot's core realism is also its core limitation, and that limitation is not a moral failing. It is honest about what a near-term interstellar probe can do if we accept extreme engineering. It can likely fly through, take snapshots, and send a few packets home if pointing and power cooperate. It cannot stop, map in detail, or become a long-lived observatory, because those require braking, mass, and time. This is where the earlier chapters echo back, and the echoes feel deliberate. We tried to escape the rocket equation by leaving propellant behind, and the universe answered with optics and power. We tried to escape biology by leaving humans behind, and the universe answered with fragility and communication. Yet physics keeps the bill, and the bill arrives as infrastructure, materials, and precision. Things that are real, expensive, and slow to build. The laser array is not just a scientific instrument, it is a civilization-scale project, and that scale changes the story. It demands capital, land or orbit, international coordination, and decades of stable funding, because you cannot build it as a weekend experiment. It also demands safety and governance, because a misused array is a strategic threat, and even a misunderstood array is a political crisis. The politics are not separate from the physics, they are part of the design, because permission is a constraint. There is historical gravity in that, because big science has always been tied to big institutions. Telescopes grew from backyard instruments to mountaintop observatories, and then to space telescopes that required national budgets. Particle accelerators became rings of nations, because no single lab could carry the load. Starshot sits in that lineage, except its instrument is not just a detector, it is a driver, and drivers make people nervous. Breakthrough Starshot built momentum early through workshops, concept studies, and public milestones, and the momentum mattered. It helped normalize laser sailing as a serious topic, not a fringe speculation, and that shift changes what engineers feel allowed to propose. It seeded research into sail materials, phased arrays, and miniaturized electronics, which has value even without a launch. It also revealed how quickly the difficulty compounds when you leave PowerPoint and when you try to close the numbers. Over time, the program faced the predictable squeeze, and the squeeze was structural. Technical unknowns remained large, and each unknown implied expensive experiments, because you cannot simulate everything at these intensities. The infrastructure price tag stayed vague, yet obviously massive, and vagueness is poison to long-term planning. Competing priorities and limited philanthropic patience narrowed the path, because even visionary funding has horizons. After 9 years, the program entered an indefinite hold, and the word indefinite carries its own chill. The idea did not die, but it stopped being a countdown, and that distinction matters. That pause is not a scandal, it is a signal, and signals are what documentaries listen for. Interstellar ambition can be scientifically sound and still be institutionally fragile, because institutions are made of humans, and humans change their minds. Starshot becomes a symbol in the narrative because it is the least science-fictional fast star concept we have, and that is why it hurts. It uses known physics and plausible components, and it does not require new particles or new dimensions. Yet it still requires a scale of coordination that we rarely sustain, especially across decades. It still requires tolerances that we rarely achieve, especially at kilometre apertures and terawatt pulses. It still requires patience that outlasts news cycles, and patience is not a technology. The deeper lesson is that interstellar flight punishes half solutions, and it does so with a kind of elegance. If you solve propulsion by beaming energy, you inherit pointing and optics, and those are as hard as engines in their own way. If you solve mass by shrinking the craft, you inherit communication and fragility is unforgiving at relativistic speed. If you solve time by going fast, you inherit the inability to stop, and stopping is what turns a flyby into a presence. And the inability to stop is not a minor detail, because it defines what mission means and what success can honestly claim. A flyby can confirm planets, sample dust, and measure fields, and those are real scientific wins. It cannot build a base, repair itself, or wait out a flare season, because it has no time and no shelter. It cannot carry the redundancy that Chapter 4 demanded for survival, because redundancy is mass, and mass is the enemy. Laser sails therefore answer one question and sharpen another, and the sharpening is the point of this chapter. They suggest that we might touch another star with machines within decades, if we are willing to build the beam and accept the risk. They also show how far we are from arriving in any meaningful sense, because arrival implies control. The nearest star remains near only if you accept a fleeting pass, and if you call a blur a visit. This is the pivot point for the whole documentary, and it is meant to feel like a door closing softly. Probes can be expendable, and their mission can be a sprint, because we can afford to lose them and try again. Humans cannot be expendable, and their mission cannot be a sprint because lives are not iterations. Humans must arrive, slow down, and live in a system that does not care, and that indifference is the true antagonist. So the central question returns with new clarity, and it returns heavier than before. What would it truly take by real physics and real engineering to send humans to Proxima Centauri? Not as a gesture, but as a mission. Laser sails show how hard it is even to send a gram, even to send a wafer with a camera. A human mission must multiply every requirement, then add the demand of braking and habitation, and then add the demand of being wrong-proof. The hook becomes darker, because closest is still a trick of perspective, and perspective is cheap. Proxima is close enough to tempt us, yet far enough to punish every shortcut, and punishment here means decades lost. Starshot's pause is not a failure of imagination, it is a measurement of reality, taken with the only instrument that matters, time. If we cannot sustain a program to send a gram, what does that imply about sending a city? We end this chapter with a hard transition. With probes, we can maybe fly by and steal a few images, if our beam holds and our sail survives. With humans, we must build a complete mission architecture that can accelerate, shield, brake, and endure, and each verb hides a universe of engineering. The final chapter asks what that architecture looks like when every constraint is allowed to be real, and when the romance is forced to become a plan. Proxima Centauri stays the next door of the cosmos, yet every honest calculation still stretches beyond a lifetime. On a star map it sits like a neighbour's porch light, close enough to point at, too far to walk. Chapter by chapter, we chased speed, then survival, then arrival, and each gain exposed another cliff. Start with the benchmarks that refuse to flatter us. Voyager 1, drifting near 17 kilometers per second, needs roughly 73,000 years to reach Proxima. In visuals, it's a pinprick leaving the sun's glare, then fading into black where calendars lose meaning. Parker Solar Probe, faster than any human-built craft at over 190 kilometers per second, still implies about 6,700 years. Even that record holder is only fast because it falls deep into the sun's gravity well, then steals a little speed on the way out. Those numbers are not trivia. They are the baseline verdict of our current civilization. They also carry historical weight, because our fastest probes were built for exploration inside one star's domain. To make the trip human, we must reach a high fraction of C, then hold a crew alive for decades, then slow down. The order matters, because each step reshapes the next. The 0.1c thought experiment is the cleanest mirror. At 30,000 kilometers per second, the cruise is a little over 42 years one way, before margins, detours and failures. In the mind's eye, the sun shrinks into a bright star among many, while the ship's world becomes a sealed cylinder of light and recycled air. That timeline already assumes an engine class we do not yet operate reliably. It assumes power levels that belong more to grids than to spacecraft, and it assumes we can reject waste heat without unfolding impossibly delicate radiators. Now add the part that doubles everything. Deceleration is not a separate feature, it is the other half of the mission, and it demands comparable delta V. If you accelerate to 0.1c and then brake to arrive, you pay the energy twice and you carry the consequences twice. In practice, braking is where elegant sketches turn into brutal bookkeeping, because momentum does not negotiate. A flyby is not arrival, and it cannot become settlement by optimism. At 0.1c, the target system is crossed in days, and the habitable zone becomes a thin ring you slice through. The camera would barely have time to pan. One bright star, a few moving points, then darkness again. Science becomes snapshots, and human presence becomes impossible without braking. Even robotic instruments struggle, because high-speed imaging fights motion blur, limited downlink, and the simple fact that the encounter is over almost as soon as it begins. Every propulsion solution creates a new cascade. Rockets that carry propellant collide with the rocket equation, where mass ratios explode and payload collapses. The math is unforgiving, because every kilogram of fuel needs more fuel behind it, and the stack grows like a pyramid. Nuclear pulse and fusion trade propellant limits for neutron damage, radiator mass, and reliability across tens of thousands of critical events. Historically, these ideas have been revisited for decades, not because they are easy, but because they are among the few that even touch the required energy density. Beamed propulsion dodges carried fuel, then demands civilization-scale infrastructure and impossible precision. A laser array big enough to matter would have to hold its aim across astronomical distances, through jitter, diffraction, and the slow drift of orbits. Laser sails can plausibly push grams to 0.1c or more, but they cannot easily stop. The moment you ask a sail to brake, you inherit huge structures, long interaction times, and fragile control. You also inherit a navigation problem where milliradians become millions of kilometers, small errors that grow into missed stars. If propulsion buys decades instead of centuries, survival becomes the dominant clock. A crewed ship is not a vehicle. It is a closed industrial ecosystem that must run for 40 years without resupply. Air, water, and nutrients must cycle with near-planetary stability, while filters clog, pumps wear, and seals age. Life support becomes a reliability problem where small leaks, sensor drift, and microbial surprises compound into mission-ending cascades. The visual shift from engines to maintenance, hands in gloves, panels open, the quiet labour of keeping a world alive. Radiation makes the accounting harsher because it charges interest every day. Galactic cosmic rays are hard to shield without creating secondary showers, and solar particle events demand a storm shelter that must always work. The danger is invisible, but dosimeters would tick like metronomes in the background, quietly counting damage. Active shielding promises a mass-light umbrella, then demands superconductors, cryogenics, heat rejection, and fault tolerance for decades. The ship must be both a habitat and a laboratory, because the environment itself is an experiment. At high speed, dust turns into ballistics. The interstellar medium is thin, but the path length is enormous, and impacts become expected rather than rare. A grain the size of sand at a tenth, the speed of light, carries the energy of an explosive charge. Forward shielding must be sacrificial and layered, and every ton of protection becomes another ton to accelerate and cool. In visuals, the bow becomes a scarred shield face, ablated, replaced, and watched like a patient's vital signs. Human biology is the quiet limiter that does not negotiate. Decades in microgravity degrade bone, muscle, and cardiovascular function unless artificial gravity works reliably. Rotation helps in theory, yet it introduces its own engineering compromises: bearings, vibration, and the delicate balance of a spinning home. Aging continues, fertility and ethics collide, and medical capability must be carried, maintained, and trusted without evacuation. The question is not only whether we can survive, but what kind of society we become inside a sealed hull. Autonomy is not optional because light itself delays help. Communication lags by years, so diagnosis, governance and repair must be local. The ship needs procedures that survive grief, conflict and cognitive drift, because a small human failure can trigger a systems failure. In a world where messages arrive as history, the crew becomes both mission control and civilization, accountable to no immediate outside correction. This is why generation ships and suspended animation keep returning in serious discussions. They are not fantasies of comfort, they are responses to time and biology. A generation ship accepts the decades by turning them into a lineage, then must solve education, purpose and consent across people who never chose departure. Suspended animation promises to compress subjective time, yet it leans on medicine we have not proven safe for years, much less for a lifetime. They also introduce new risks, from social stability to unproven medicine, and they do not erase shielding or braking. So the final accounting has 3 stacked barriers. First, reach high fractions of C with power and heat rejection we can actually build. Second, protect humans and systems from radiation, impacts, and entropy for decades. Third, decelerate and arrive with capability intact, not as a fleeting flyby. Each barrier is a gate, and each gate is locked by physics rather than ambition. When any one layer fails, the mission fails, and the layers are coupled. More shielding increases mass, which increases propulsion demand, which increases waste heat, which increases radiator area and vulnerability. More redundancy increases reliability, but it also increases mass and complexity breeds new failure modes. The ship becomes a web of trade-offs. Pull one strand, and the whole design shifts. Near-term progress still matters, but it looks different than a launch date. Radiation mitigation can improve through better materials, better dosimetry, and smarter habitat geometry. Even simple choices like placing water tanks and supplies around living quarters can turn necessities into protection. Closed-loop life support can mature through long-duration ground tests, robust sensors, and maintainable designs. The goal is not perfection, but graceful degradation, systems that fail slowly, visibly, and repairably. High-power space energy systems can be developed for propulsion experiments and deep space industry. Fast precursor probes can map dust, fields, and space weather, and they can validate navigation and autonomy. In visuals, tiny scouts race ahead, silent darts measuring the darkness we plan to cross. Each step reduces unknowns, but none removes the need for simultaneous breakthroughs. The cosmological perspective is the final constraint, and it is not sentimental. The speed of light is not just a limit, it is a shaping force for civilizations, separating worlds by time as much as distance. Even at 0.1 C, the nearest star is not a trip, it is a long-term project with no quick revisions. Interstellar space turns travel into a commitment across generations, and it punishes species that cannot sustain long projects. So the central question resolves into a sober answer. Proxima Centauri is the nearest star, but reaching it with humans requires mastery of energy, materials, autonomy, and long-term human survival at once. The universe is under no obligation to make those breakthroughs arrive together, or arrive in time. We can dream with precision and still be trapped by the arithmetic. Closest is a trick of perspective on a galactic map. In human terms, Proxima is an ocean of time, energy, and vulnerability. To cross it, we do not need one miracle, we need a transformation in what we can build and what we can endure. And the deeper question lingers, what would it mean to arrive if the journey changes us first? Across this journey, 4 light years stopped being a poetic number and became an audit of speed, mass, heat, and time. We watched familiar rocketry collapse under the rocket equation, then saw near-possible engines, nuclear pulse and fusion, trade propellant tyranny for neutron damage, radiator sprawl and civilization-scale logistics, and when beamed light finally dodged the mass ratio, it exposed the next cliff, because a fast flyby is easy compared with braking, shielding, and keeping a small world alive for decades. The deeper revelation was that interstellar travel is not one problem, but a coupled system where every solution multiplies another cost. Acceleration demands energy, energy becomes waste heat, heat demands radiators, radiators add area, area invites impacts, impacts demand shielding, shielding adds mass, and mass drags you back into the very equation you tried to escape. Meanwhile, the crew is not cargo, but biology. Aging, adapting, and sometimes breaking under radiation, microgravity, isolation, and the slow entropy of machines that must not fail. So Proxima Centauri is closest only in the way a shoreline looks close from a cliff, until you measure the water. At 0.1c, the trip can fit inside a human career, yet the moment you insist on arriving, slowing down, surviving the dust, enduring the cosmic ray drizzle, maintaining a closed biosphere, governing a society with no rescue and no real-time Earth, the distance expands again into something more like an ocean of vulnerability. The nearest star doesn't just test our engines, it tests our ability to build systems that remain trustworthy for 40 uninterrupted years. That is why every chapter kept returning to the same hard symmetry, the double energy tax of going fast and then paying again to stop. Carry the braking propellant and you drown in mass ratios. Refuse to carry it and you must invent a destination brake. Mag sails biting the interstellar medium, photon sails pushing against starlight, plasma interactions with Proxima's wind, each one elegant on paper and brutally sensitive to conditions we can barely measure from here. Even if propulsion becomes plausible, we still have to prove in the real world that closed-loop life support can be self-sustaining, that active shielding can run for decades without catastrophic failure, and that a crew can remain competent, accountable, and humane when Earth is years away by radio. And hovering behind the engineering is the institutional question Starshot quietly revealed, the one no equation can ignore. If a gram-scale probe strains budgets, politics, and dual-use fears, what happens when the project is a moving nation-state made of reactors, radiators, and weapons-adjacent power systems? Interstellar flight is not only a technology challenge, it is a continuity challenge of funding, governance, safety, and patience across generations that may never see the launch become a landing. So what would it truly take to send humans to Proxima Centauri? And why does the nearest star still break our numbers? It would take not a single breakthrough, but a synchronized transformation, propulsion that reaches a meaningful fraction of C, braking that does not demand impossible propellant, shielding that turns space's invisible storm into manageable risk, and a closed world that can repair itself, govern itself, and endure. The nearest star feels like a different universe because, by honest physics, it forces every weakness to show at once. Closest is a trick of perspective, near on a galactic map, but far in the currencies humans spend: energy, reliability, and fragile years of life. In the end, Proxima Centauri is less a destination than a mirror, reflecting the limit of what we can keep alive, coherent and safe, while everything around it tries to unravel. If we ever arrive, the triumph will not be that we crossed 4 light years, but that we learned how to carry a civilization through the dark without breaking it. And until then, the most honest interstellar mission may begin with what we can already harden, miniaturize, and send first, because probes are how we practice, and practice is how the impossible becomes merely expensive. If we want next door to mean something human, we should build the stepping stones now: deep space habitats, closed-loop biospheres, high-power beaming, and radiation protection, and test them until they stop being dreams.